Okay, I would like to thank, it's okay? Gregory and David for this kind invitation to speak here in this beautiful place. I want to talk about mixed order phase transitions, and particularly in the end I'll talk about extreme value statistics in these kind of systems. And this was work which was done by together with Amir Bar, formerly my student, and together with Satya and Gregory, who are here. Okay, so what are mixed order phase transitions? These are transitions which have nature which is both of type first order and second order. It's kind of mixed in the sense that they have a diverging length, like at the transition, like in a second order phase transition, and the length psi can diverge either with some power law of the parameter that goes into the transition, like t to the minus nu, as we expect, but sometimes it goes exponentially, depending on the model and the system. But on the other hand, so this is like second order phase transition, but on the other hand, there is a discontinuity in the order parameter. That is, there is a jump in the order parameter that describes the system, like in a first order phase transition. It turns out that this is rather common. It appears in quite a large number of systems. I was surprised to see how big a class of systems this is. And let me just give a few examples. One example is this DNA denaturation, which the system is just the following. DNA schematically, you have two strands, then they are coupled to each other by these hydrogen bonds. And as you heat it up, you start forming bubbles. Some of the bonds, they just break up, and you form these loops or bubbles. And eventually, at some temperature, they just separate. The two strands separate, and that's a phase transition. And it turns out that this phase transition is of mixed order nature, in a sense, in the following sense. This is the typical model that people use to study this kind of system. One is the order parameter, if you want, is the discontinuous, in a sense that as you increase the temperature, you form more and more bubbles. But at the transition, it turns out that these bubbles don't grow to infinity, but there is a finite fraction of the system which is still bound, and then all of a sudden it becomes unbound. And that's in that sense, there is a discontinuity in the order parameter, which is the bound pairs, the fraction of bound pairs. Okay? On the other hand, there is a diverging length. That is, if you look at these bubbles and you look at the distribution of their length at the transition, it goes like e to the minus L over xi. There is with some algebraic correction, but there is a xi, there is a length, and this length diverges at the transition. So there is a diverging length and there is a discontinuity.
Excuse me, this order parameter that you just described in words is, can you build a Landau-like functional?
Yeah.
This serves as the order parameter.
Yeah, of course, but we'll get to it. Okay, we'll get to it in a minute. And then there are many other systems. And another very simple system is this Ising model with long-range interaction. If you take the Ising model in one dimension with interaction that decays like 1 over r squared at large distances, then that's the Hamiltonian. It turns out that this model shows a transition into a ferromagnetic phase at some finite temperature, and it's of mixed order nature. That is, the magnetization jumps at the transition, and on the other hand, there is a length, and the length diverges, in this case, exponentially. Okay? I will not talk about this system a lot because I'll get back to it in detail in a few minutes. Then there are many other examples. Jamming transition in kinetically constrained models by, a model by Toninelli, Biroli, and Daniel Fisher. I don't want to describe too many of those. There's bootstrap percolation. That's another class of models that show mixed order phase transitions. Then there is extraordinary transition by, introduced by Zia and co-workers. And Martin here was talking about in a dynamical model of Ising, hopping, and many others. I will not get into details, that's not the issue. Okay, there's a two-dimensional models that show it in percolation, etc. So what I want to do is to introduce a simple, exactly soluble model for which shows this mixed order phase transition, which puts several systems in context. That is, you know, as I said, some of the in some cases the length diverges algebraic, you know, with power law. In some cases it diverges with exponentially. So I want to put this in some simple framework. And at the end, I'll talk about extreme value statistics in such models of the domains that describe the system. Okay, so let's go on. Okay, so I'll do it in this context of the what I call inverse distance square Ising model. That is, again, the model I just talked about a few minutes ago, one-dimensional Ising model with interaction that decays with the power law, particularly with power 2. Now, in general, if the power is I minus j to the power alpha, then we know that if alpha is between 1 and 2, there is a phase transition in the system. Right? For alpha above 2, it's like short-range interaction. With alpha, this power law here, between 1 and 2, there is a first-order transition. And the interesting case I'm going to talk about is alpha equals 2, which is particularly, specifically at the borderline between this and that. And it's easy to see, there is a very simple argument to see that for alpha between 1 and 2, you should have order, you know, order in that system. The way to see it is very trivially. You take a system with all spins up. You take the system is of length capital L. You take a domain of size little l and flip it up and ask what is the energy of that. And if the alpha is larger than 2, then the energy of flipping that is of order 1. So it's like short-range interaction because you pay only at the boundaries. On the other hand, if alpha is between 1 and 2, you pay something which is some power of L. You know, it's L to the 2 minus alpha. And therefore, the system can sustain long-range order at low temperature. So, and this model has been discussed a lot by people, you know, in the 60s, you know, Anderson and Dyson and Towles and many other people. Okay. Now, for alpha equals 2, the story is the following, that the model has a magnetization M, and it's discontinuous at Tc. This is known as the Towles effect. It was conjectured by Towles with some not so correct argument, but then it was made rigorous by Eisenman later on in the 80s. The correlation length diverges exponentially, e to the 1 over square root of t minus tc. This is some RG argument by Cardy. And the phase diagram is like that. If you take the model at the magnetic field and temperature, it just phase diagram like a simple Ising model, second order phase transition, except that at this point the transition is first order. Okay? So there is a jump in magnetization here, and okay. This is unlike usual first order phase transition. In first order phase transition, you expect phase diagram that goes like that, that from this point, since it's a first order point, there is first order line coming up here, so the transition from here to there is through some discontinuity. Okay, that's okay. What I want to do is to introduce an exactly soluble, okay, this model is not exactly soluble, but these features could be proved in some way. What I want to take a simple modification of the model and to show that you can really demonstrate this feature. It's exactly soluble model, and to put things in perspective of when do you expect to have algebraic at power law divergence of the correlation length or exponential, etc. So the model is very simple. It's a little modification of the model I just described. So there is it's Ising model in one dimension with 1 over r squared interaction decay, except that it's truncated. That is, in any configuration, this interaction holds only within a domain. A domain, if you take a domain of all plus of all or all minus, only the spins within these domains interact with this kind of interaction. For example, a spin here and a spin there don't interact directly. Okay, so that's the model. There is a truncation. On the other, and there is also nearest neighbor interaction. Okay, basically. So that's the model. On the face of it, it looks like it's a truncated interaction. So why do you have order? Except that when you get close to the transition, these domains become larger and larger and larger, and therefore, effectively, it's a long-range interaction. Okay. Also, one point to consider: this is basically this model. I described it in words here, but basically it's a many-body interaction. That is, two spins interact depending on whatever the spins in between do. So therefore, it's in fact it's a many-body interaction. Okay, spin here and the spin there basically have to know that all the spins in between have the same sign to interact. Okay, so it's okay. Okay, so the results. Okay. That for this model, I just want to summarize the results. First of all, the model can be solved. There is a critical point, there is a transition, and the correlation length diverges algebraically with some exponent nu, and nu is non-universal. It depends on the details of the model. So it's roughly like that. There is its extreme Tauless effect, namely. The magnetization, Tauless effect is the effect that the magnetization jumps at the phase transition in this model. That's called the Tauless effect. Here, this extreme Tauless effect in a sense that the magnetization jumps from 0 to 1. Okay, that's basically, okay. Then the phase diagram in a magnetic field looks like that. There is, it's like ordinary first order phase transition, not like this other one. There is these wings. It's very closely related to the models of DNA transition. I may say a few words about it. And at the end, I want to talk about the statistics of these domains, of the large domains that goes there. Okay? Okay.
The divergence, is it symmetric on the both sides of the transition, or it's on one side? The divergence of the correlation length?
The divergence of the correlation length, it's the distribution of the size of the domains. It's coming from above. Yeah, it's coming from above. Yeah. Right. Okay. Now, so here is the. Okay, to look at the model, it's interesting to look at some alternative representation of it. If you look. The energy of, if you write down the energy of a single domain, suppose you have a domain of length L, and what is you sum up all the interaction within that domain, okay? You see that the energy of a domain of length L goes like there is a linear part in L, but there is also a logarithmic part, okay? So I can sum up the interactions within a domain, and I get a logarithmic part in the size of the domain. So basically, I can describe the domain as by the edges of the domains, right? It's like you have charges here, and basically these are the domains, and all I need to know is basically the length of these domains, and the Hamiltonian of is basically can be written as okay, the configuration is just given by the LIs, by the length of these domains. Okay, it's a series of domains. And then the energy is just the sum over Li. And there is a logarithmic part, log of Li. And there is a chemical potential that is gives you, n is a number of domains, okay? Because that's also a variable. So I can just look at it as if I have charges distributed on the line, and they interact logarithmically, but they interact logarithmically only with nearest neighbors. Okay, so this and that interact logarithmically with each other, but this charge does not interact directly with that charge. Okay, and there is a chemical potential that controls the number of charges that you have in the system. Okay. Okay, and this comes from the nearest neighbor interaction. So basically, that's the model, and the model is this representation is very useful if you want to look at renormalization group and study it, because basically it's like charges which like charges in 2 dimensions, right? They interact logarithmically, but they are placed on a line. They are restricted to move on a line. So basically the Kosterlitz-Thouless type of thing appears here. I'll say a few words about it in a few minutes. Okay. Okay, so the analysis of the model. So the way to analyze the model, you can calculate the partition sum, which is just you write down the weights of each domain, which is from the logarithm, except that you have the constraint that the sum over Li's, the Li's is the length of the domain, has to be L, okay? And the way to do it is just to go to Grand Canonical, introduce fugacity, calculate trivially the Grand Canonical partition sum, which is explained which is given in terms of this U. U is just the partition sum of a single domain, basically. And this is the polylog function. So once you have that, you can invert it, you can calculate everything. That's the way to analyze it without getting into details. So what you have basically to do is, if you want to calculate, to find the phase transition, you have to look at the the pole of this, the pole in the fugacity of the Gantt partition sum, and the pole, the Z, gives you the free energy, basically, e to the beta f, once you know that. And the phase transition is obtained in this way. If you look at this function, it has a branch cut at some value here. When the pole is appears, this star appears, takes place at this point, it's okay. As you change temperature, this pole just goes towards the branch point. When it hits the branch point, you get the phase transition. That's the schematic way to get the phase transition. Okay, that's it. So if you look at the nature of the phase transition, you can calculate it right from here. The probability of having a domain of length L, little l, is, I think Martin discussed it yesterday, some other people discussed it. It's z to the L minus L divided by z to the capital L times the probability of having a domain of length L, which is this. And it's easy to see that the probability of having a domain of length L is just go e to the minus L over xi divided by L to the c. This is the form. And the xi and the c is just some parameter that depends on the critical point or whatever. So it's a continuously, it could be anything, it's some parameter. And xi is the correlation length. You can analyze the way the correlation length diverges near the phase transition from the properties of this polylog function. And it turns out that xi diverges like t to the minus nu, where nu is given by 1 over c minus 1 if c is between 1 and 2, and it's just 1 if c is larger than 2. So you get a power law divergence of the correlation, and it's non-universal in a sense that it depends on this parameter c, and c is a parameter which depends on the critical temperature. So it's a really non-universal. You can get anything you want in this model. Okay. Now there is 2 other parameters that you can talk about this model. One is the number of domains, okay, per unit length, okay, n over L. And the other one is the magnetization. You see, the transition is that the number of domains decrease towards when you get to the transition. It can go to 0, basically to 1, if it's second order phase transition. You know, the length of the domain goes to infinity, or it can stay finite. Okay, so that's one order parameter, and the magnetization itself is another. Okay, and n the number of domains is 1 over basically 1 over the average length of a domain. And the average length, since at the transition psi goes to infinity, it's just given by this thing. So if C is between 1 and 2, the length diverges at the transition, while if C is larger than 2, it stays finite. So basically that's the so if C is between 1 and 2, n goes continuously to 0. That is, the number of domains go to 0 continuously, and it's kind of second order phase transition. On the other hand, if C is larger than 2, it's discontinuous, and you get a jump. That is, you get some distribution of domains, and you change the temperature a little bit, and then it becomes a single domain. Okay. The order parameter is like that, is the magnetization, and basically it's -1 to the I Li, because the domains change magnetization from one to the other. And it's clear that if T is larger than Tc, you have many domains, and clearly it just, there is no by symmetry, M is equal to 0. The number of up domains is equal to the number of down domains. There is no correlation between them. On the other hand, if T is less than Tc, then there is a single domain. So it's either this or that, and you get M is equal to 1. So it's a really extreme Thouless. That's what I called here extreme Thouless effect. Phase diagram. Okay, I will not. Okay, that's very simple. As a function of temperature, M is 1 here and 0 there. In the Tc plane, there is a line, and it's n is this n. M is 0 here, M is 1 here, and the number of domains changes continuously here and discontinuously there. That's the phase diagram. And the phase diagram is, if you put a magnetic field, is like that. That is, you still have these wings as in ordinary first order phase transition. Now I want to say a few words about canonical analysis, because I think that's an interesting. You can do a canonical analysis by, you put, you have the fugacity Z, and you have another parameter associated with n. You have two variables, L and N, and you can go to parameters Z and Q, which are the fugacities associated with them. The ground partition sum for Z and Q can be calculated. It's this, and then it can be inverted. So it's the usual stuff that we are used to. And it turns out that we can calculate the free energy as a function of n, of the number of domains. And when you do that, it turns out that you get a saddle point, and n is equal to the number of domains. It's just equal to mu is the polylog function, and z is the fugacity, and that's the expression. And it turns out that if the free energy, if n, there is a critical value of nc. If n is larger than nc, it looks like that, where z is the fugacity associated with the system. On the other hand, for n less than nc, the fugacity just stick at the pole, and it's just given by a constant. So for n less than nc, the free energy, this is just a constant. It's a linear function of n, because the fugacity is just stuck at the pole. On the other hand, if n is larger, it's this star is a function of n, and it's a more involved function. So pictorially, it goes like that. If you look at the free energy as a function of n, it goes like that. The critical point is t equals 1. So if you go above the critical point, so t is 1.1, you get this kind of curve, and the minimum is obtained somewhere here, and n is just the minimum of that, and you get the number of domains. As you change the temperature, basically the slope of this linear part just changes. It becomes horizontal at some point. That's a phase transition. And you get the first order phase transition from n at that point to n at that point. And that's the usual first order phase transition that you expect. This is, of course, if c is larger than 2. Okay? Now, so why do you get critical behavior? Why do you get diverging length and whatever? This comes from finite size effect, basically. Typically, when you have a first order phase transition like that, okay, let me just draw it here with the chalk. You know, you have two minima and like that, and then this is replaced by, you know, the common tangent, and basically the free energy in the end looks like that, right? And you go from here to here. Now there is a barrier here. Now the barrier typically in the first order in a system like that, it goes like L to the power d minus 1. If you have a system of size L in d dimension, it goes like L to the d minus 1. Why? Because if you start with a system and you have to create a domain wall, and in order to go from one state to another, okay? Suppose you have two states, A and B, and you want to go from one to, you create a domain wall, and once the domain wall is there, you can just shift it and you go from A to B. Now the energy price, the free energy price to pay for a domain wall is d minus L to the d minus 1, all right? Because that's the price. Here d is 1, so basically you pay a logarithmic price. It's log. So if you look at, if you look at this is a finite size effect. So when I say that this is flat, it's basically flat up to this. And this bump here grows logarithmically with the system size. And therefore, you can get some fluctuations, and that's why you get this kind of behavior in this system. Okay? A similar thing happens for the magnetization. The magnetization at high temperature looks like that. You increase the temperature, then it becomes flat. But this flat, again, has some finite size effect in it, which I don't want to discuss anymore. Okay. I want to say a few words about renormalization group and then go to extreme value statistics of the domain size. You see, how come you have here, sometimes you can, in this model, you have algebraic divergence of length. How can you get also exponential divergence in this kind of systems? So, as I said, basically the model it can be represented as charges which are on a line, and there are two-dimensional charges in the sense that they interact logarithmically. Now, you can just write down the partition sum of this model, introduce some fugacity. You know, you have a fugacity to tell you how the density of charges and the interaction between them, which is logarithmic. So in the z, just the power law of zi plus 1 minus zi. Again, only nearest neighbor interaction appear in this system. So when you do renormalization group, let me just very schematically just say it. Typically, you take two charges, the two close-by charges, you know, you renormalize, and you look at the effect when you take them out on how they change the interaction between the charges nearby. Now, in this case, since the charges interact only with nearest neighbor, so it's not really a dipole, right? Because this charge, this plus, does not interact with this plus, and this minus does not interact with this. So I can shift them, and basically that almost doesn't cost any energy. And as a result, when you renormalize and you take out this pair of close-by charges, they don't contribute to the interaction between the effective interaction between these two charges, but they contribute only to the fugacity. So as a result, the renormalization group equation, X is basically C. C is the interaction, right? That's the coefficient of the log of the interaction between the charges. So the renormalization group of this renormalizing this, which contribute y squared, fugacity squared, they go into the fugacity term. So basically, these are the renormalizations group scheme of that system. On the other hand, if you have Kosterlitz-Thouless, where all charges interact with all charges, this is a dipole, and therefore they renormalize the interaction between these two charges. And as a result, if I want to compare, in the Kosterlitz-Thouless case, when all interact with all, the y squared term enters into the renormalization equation of the interaction, while in this case, it enters into the renormalization of the fugacity. So that's basically the only difference. So if you look at these two flow diagrams, you get the usual Kosterlitz-Thouless in one case, while in this case that I'm talking about, there is an extra line of fixed points here, and that corresponds to the phase transitions we are talking about. In the Kosterlitz-Thouless case, you get only that point as the transition point, and since the flow here is nonlinear, then you get the usual Kosterlitz-Thouless exponential divergence of correlation length. Here, it's a usual phase transition. There is a line of phase transition. Each one corresponds to a different value of C, and that's why you get non-universality of the exponent nu that I described. It appears here. Okay, so that's very schematically. I just wanted to show you that that the difference between this exponential divergence and algebraic divergence comes because of the truncation of the interaction restriction to nearest neighbor, basically. Okay. Basically, that's what I want to say here, and I want to talk a little bit about extreme value statistics in these models. Now, in these models, they are composed of these domains, which are pluses, minuses, pluses, and minuses. And the question is, what is the statistics of the largest domain? Okay, and last few days we got a very nice introduction to this, very beautiful talks by Satya, by Claude, by Eli Barkai, and this basically set up the stage for this. So if the domains are really independent, if the probability of having a domain of length L1, L2 is just independent, it's just a product, then you will get the usual, three universality classes that we have, the Weibel, Gumbel, and Frechet. Here, on the other hand, there is a little bit a twist. The lengths are constrained, as in other studies that Claude described in the first day. The length is constrained so that the sum over L and is just L. But also the number of domains is fluctuating, and it's controlled by a fugacity delta. So there is a fluctuating number of variables controlled by some parameter delta, and also they are constrained. And this gives some difference in the behavior of the extreme value statistics in this case. And let me just summarize the result that we have. So basically, P of ln is just given by this. It's E2, and that's what we have. So the way to calculate it, the cumulative distribution function is usually described here before. You calculate W0 of x given L. That's the cumulative distribution that all domains are less of size less than L. You can do that. ZL is the full partition sum, and basically the ratio is just gives you the probability that you have that the maximal domain size is less than x. Okay, so that's, you calculate it, and then you invert, calculate W of x and z, you invert it, and that's how you can calculate it. And then let me just give you the result. It turns out, and it's very easy to understand, if you are at temperatures larger than Tc, the distribution is just given by this. So it's essentially exponentially. It's e to the minus L over xi, where xi is finite. That's in the paramagnetic phase. And therefore, basically, the constraint of the length does not play any real role. It's just, these are small domains. And therefore, one gets the Gumbel distribution, as you usually expect in these things. And this B of L is just log of L plus some correction. If T is less than Tc, on the other hand, it's more natural to look at the distribution function of this is not at the cumulative, but at the direct distribution function of a single domain of at size x, and it turns out to be a function of L minus x, and this f of y, you do the calculation, is 1 over L to the power c. It just goes like that. And then it turns out that if c is larger than 2, this converges. I mean, the integral here converges, and therefore L max minus L is of order 1. So you have the average domain size. If you are less than Tc, basically you have one domain. And there are little domains which are a little bit there, but their average size is of order 1, basically. That. On the other hand, if C is between 1 and 2, because of this distribution, they are, of course, sublinear, but the average length of these extra little domains diverges with some power law of L to the power 2 minus C, but basically you have one single domain of size L and some other domains which are sublinear. Goes like that. On the other hand, on the critical line T equals Tc, if C is larger than 2, the average length of a domain is finite if C is larger than 2. And therefore, again, the constraint doesn't have much effect. And you get the Frechet distribution. Because the domain size, the average domain size is finite, and that's it. On the other hand, if C is between 1 and 2, L diverges, L average diverges, and then the constraint has a strong effect. It turns out that L max is going to behave like capital L, proportional to L, and if you calculate the probability of L max is equal to x, it turns out that it's a function with multi-singularities, that it's a function of L max over L at a half, 1/3, 1/4, etc., etc. And the reason for that is, again, very clear. It's if Lx is larger than a half, then you cannot have more than one large domain. If between 1.5 and 1/3, you can have more than two such domains, etc., etc., and you get these singularities. You don't see them here, of course. You see only the leading one, but that's a different function. By the way, this part of the curve between 1.5 can be calculated exactly. It can be it's given by some function, hypergeometric function, and this can be calculated exactly. The other ones are numerically. So basically, that's the table that summarizes everything. Above Tc, you get the Gumbel. At T equals Tc, if C is larger than 2, you get the Frechet. If it's C is between 1 and 2, you get something else, and below Tc, you get again a different distribution function. Okay, so with that, the summary. So we have these models of extreme value of mixed order phase transitions. One can understand the way using this renormalization group and charge things to see how you can get algebraic divergence or exponential divergence of the correlation length, and the distribution of the largest domain can be calculated in this case too, and to see this interesting effect. So, thank you. Yeah, Matti.
Yeah, sorry, it's not really a question. Could you just explain the curve with the singularities at a half, a third? I didn't quite understand that. That one.
Yes. You see, the probability, you know, when you look at Lmax, you know, if it's between, if Lmax is between a half and 1. So suppose what is the probability of having a domain of size 3/4, okay? You cannot have more than 1 like that, right?
Yeah.
At most 1, okay? On the other hand, if you go between half and the third, you can have 2 of them, which are, you can have 1, you can have 2, you can have, so there is something else that enters into the calculation, which is at 1/2. And that's why you get this series of singularities, because you get more, you know, you get more possibilities of having this largest domain. So basically that's where, you know, physically that's where it comes from.
Okay.
Yeah, and it's very similar to Claude discussed it in one of his examples there a few days ago. It appears also, yeah, okay.
What about the latent heat and the specific heat? How does it behave near the space transition?
Well, there is a discontinuity, you know, there is latent heat. You can calculate it. It's, you know, the energy jumps.
Right. So there must be latent heat. What
Yeah.
about the specific heat on the symmetric side? It diverges?
Oh, I don't remember. I guess so, but I'm not. I have to look at it.
It's just,
Yeah.
is there any relation between the exponents?
Yeah, right. But there is a discontinuity in the heat already. You know,
Right.
there's a stronger effect. I don't have the picture in my mind. Okay.
This model of your charges, like alternate charges, plus
right,
and minus.
right.
So if I take fixed number of them and put it in some potential, harmonic potential, or
Right.
something, do you know how like density profile will
Yeah,
be?
there is. I think Anupam will
Okay.
talk about it.
But with the alternate sign.
No.
I'm saying because your charges are with alternate sign, right? Plus
Right.
and
In
minus.
our case, yeah.
Not the same charge, but the
Yeah, I
alternate
understand.
one.
No, then. Yeah, here it's attractive interaction.
Yeah.
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 Okay, I don't know.
Oh.
Okay.
Okay, so if there are no other questions, let's thank David.
Okay, so let me start by thanking our dear organizers Gregory and David, and thank you very much for inviting me, so such that I will have a chance to present our pretty recent work. It's few works combined together with the same streamline, which we did basically within 1 year from now, maybe even less. And I will talk about spectral properties of a single trajectory of random motion. So let me start with some motivations for the works and definitions. So in textbooks we can find a sort of Fourier transform of a single realization of a stochastic process which is defined here. It is integral over time domain or spatial domain. It depends on the circumstances. So you integrate from 0 to t. Here you have exponential of I f t, f being frequency, I is square root of -1. Here is our stochastic process. Then after integrating, you take the absolute value, put it in square, then you average over many realizations, and presumably that's also a good thing to go in the limit of observation time or integration time equal to infinity. Now, if you talk really about experimental application of this property, which is called power spectral density or spectral density in some instances, then there are two evident shortcomings of such a mathematical definition. First is that it is not possible, of course, to go to an infinite observation time. We don't live so long. And second, it is not possible to make a big enough statistical sum. In some, if you do some experiments in vivo and you observe something moving in a cell or somewhere, you cannot do it for infinity, and you cannot make plenty of realizations of the process. Actually, now the motivation of our work came from some experimental studies of Matthias Weiss from University of Bayreuth, who looked on several stochastic processes. One was a standard Brownian motion in sucrose, this blue curve here. I will show on the next slide a bigger version of this figure. Second was anomalous diffusion in dextran solution, viscoelastic solution. This is curve above. And these are numerical simulations results for standard BM Brownian motion on a square lattice. And second, it is for Brownian motion on percolation cluster. And here it is plotted this value power spectral density as a function of frequency, and average is taken just over 3 trajectories. So here I made a bigger thing such that you will see that there is a very strange thing, because 3 trajectories, it's not an average. It's not a statistical sample. And if you do something like random walk and you look on mean square displacement, you know that average based on 3 realizations will be pretty noisy. These curves are much more smooth. Of course, they fluctuate, definitely. But these experimental do fluctuate, of course, that you cannot measure precisely the location of the particle. There is an intrinsic error which is incurred by just some intrinsic apparatus which you use for make measurements. In numerics, of course, it should be smoother, and we did indeed see that it is smoother. Sorry. For blue curves, which correspond to standard Brownian motion, you see the spectrum which goes like 1 over frequency squared. They use a different definition, I cannot change them. So this is frequency. And you see a pretty good slope. And the same here. And you see an anomalous slope basically for diffusion on a percolation cluster as well, a good trend. And now the question is that based on just 3 realizations, we observed quite a robust trend. And the question is, what was prompted actually our work, is there is something behind. Yes, one may understand that Fourier transform is a sort of a filter. It may filter out some fluctuation, especially if you use high frequency limit. But still, now, what I'm going to talk here, I will focus on this random variable defined on the level of a single realization of a trajectory. And I will try to study exhaustively well its statistical properties. I will going to calculate exactly the full distribution function of this random variable, which is parameterized by frequency and observation time. Any frequency, arbitrary observation time, not necessarily infinite one, for Brownian motion. This is our joint work, which appeared already some months ago with Diego Krapf, who made some experiments for us, and Marinari, who made numerics, Ralf Metzler, Alessio Squartini, and myself, and Xinrang Xu was with Diego Krapf. He made also experiments. Then I will do the same, essentially the same for fractional Brownian motion. And here we have a little army of co-authors. Mostly these gentlemen and ladies are experimentalists who did experiment for us in different settings, in different physical systems like agarose hydrogels, dynamics of amoeba and vacuoles inside this amoeba, and dynamics of telomeres in mammalian cells. Enzo Marinari was doing heavy numerics for us, and Alessio Squarcini, Ralf, and myself were occupied with the calculations. Then I will talk a little bit about our very recent work with Satya Majumdar, where we calculated now only the first moment of this random variable, the ensemble average power spectral density, for a case of fractional Brownian motion interrupted by stochastic reset, what was the topic of talks yesterday, except that we can look on a little bit more general process, not Brownian motion, but fractional Brownian motion. And the paper appeared in JPhysA online just yesterday. And last point, if I have time, I will go out of equilibrium, and I will look on the model of so-called molecular gyrator. So something molecular motor which permits random rotational motion in out of equilibrium situations, and basically just to understand what is it is a couple of Ornstein-Uhlenbeck processes, each of which evolves at its own temperature. So let me start. The case of simple Brownian motion. So we consider Brownian motion in d dimensions. These are the components, projections on different axes. Each component on average have squared component averaged over all the realizations goes like 2 dt. D is d-dimensional diffusion coefficient. And what we are looking for on the moment generating function of such a functional. And since this is a real value process, it can be written like this. So you have sum over all components, you have double integral over 2 times, trajectory taken at time tau 1, tau 2, and you have cosine which binds them. So there are different ways of tackling this problem and just handling the average. And what we found the most simple and straightforward one, it is just to use Wiener representation of Brownian motion. It's pretty old result due to Wiener, where you use expansion in sine with shifted, and here on an interval OT big, it is our observation time, and these are random amplitudes, which are Gaussian random variables, independent from each other with the distribution, which is just this one. D is d-dimensional diffusion coefficient. After doing all maths, you arrive at the following exact expression for the moment generating function. Since we have components independent from each other, the number of components k enters just here, which is quite natural. And here we have a quadratic polynomial on lambda. Lambda, sorry, it is what stands here, Laplace parameter. And here we have, before the linear term, we have mu to mu. Mu is the first moment of the power spectral density. This is a standard thing, which is a textbook property, which is usually studied. Now, second term between quadratic, you again have mu squared here, and you have 2 minus gamma square. And gamma square is important parameter, most important for this type of problems, as I will show in what follows. It is standard deviation divided by mu. It is a little bit different of the Fana factor, which Satya mentioned in his talk, in the sense that it is a square root of variance instead of it. So it is dimensional, this property. So mu for Brownian motion is given for any frequency, any time, by this expression here. So if you take long, big frequencies or time in observation time going to infinity, you end up at just having 4d diffusion coefficient divided by f squared. Now, sorry. And this will be exact expression for the variance, valid for variance of the power spectral, single trajectory power spectral density, which is given here. If you look on the value of gamma, which is this coefficient of variation of the distribution, this stands in the limit of infinite observation time to a constant, which is square root of 5 over 2. It is a little bit less than 1, which means that standard deviation is bigger than the mean, which means that it is effectively a broad distribution. It means in turn that there is no reasons a priori to look only on the first moment as people used to do, because standard deviation is bigger than the first moment. And of course, it justifies our quest for the whole distribution function of the power spectral density as a random variables. Now, associated distribution is written here. You can invert this by taking an inverse Laplace transform. It's a little bit heavy expression. And here you have a modified Bessel function of such an argument. So it is called Bessel function distribution. It was somehow studied in something like 1930, just as a priori distribution which have a heavier tail than Gaussian one. Now let us focus on this parameter gamma. And this is, as I said, is a key property because it enters here, and we want to understand how a coefficient between the quadratic term behaves as a function of frequency. Now, we plot here this gamma as a function of logarithm frequency times observation time. We see that it starts at square root of 2, jumps and oscillates around square root of 5 divided by 2, and these oscillations fade out. And so we can say, for instance, if we may define some accuracy parameter when the amplitude of oscillations around square root of 5 divided by 2 becomes smaller than epsilon. So it happens namely when ft becomes larger than 2 divided by 5 epsilon. And if we look on this regime, on this either large observation time limit or limit of high frequencies, we can come back to our expression for the moment generating function, and so you see that this is just a number. And the only scale which appears here, which multiplies lambda, it is first moment. Nothing else. There is no more frequency dependency. The whole frequency dependency is embodied just in the first moment. So, and in this case, of course, we may associate, we may just use this fact to represent our distribution in such a form that a single trajectory power spectral density for k components divided by the first moment is equal in distribution to a certain parameter a, which is just a real number. And its distribution is given here. Which means that most likely for any realization of the process of Brownian motion, you will see the first moment, frequency dependence of the first moment, and you will have only the amplitude in this law, which will be a random number, just numerical. So if you plot logarithm, you should see the frequency dependent. You will have, as a function of the log of frequency, you will have just an array of parallel curves. Now, about some numerics. There are several ways to check our predictions and to do numerics. And one of them, if you want to draw Brownian motion as a line in continuous time. Not Monte Carlo, but continuous time curve. You may use this Wiener representation and truncate it at some n. Now, plugging this expression to the expression for the moment generating function, you may easily calculate and get exactly the same expression which has exactly the same structure for the moment generating function, with the only difference that this first moment and gamma will correspond to truncated version of the Wiener representation. And here I plot reduced first moment, and here I plot gamma as the function of ft. Black curves, it is result corresponding to n equal to infinity. Here the same, and these curves, green one and red one, just correspond to different level of truncations. For green one, I truncate at just 20 terms, and for red ones, just at 40 terms. And you see that you exactly reproduce the curves up to a point which is pi n. At this point, you have a first moment jumps downwards from 2 to 1, and the coefficient of variations jumps from square root of 502 to square root of 2. And you see that it is a catastrophe in the distribution. It jumps to a different distribution instantaneously because this coefficient becomes 0. So, but the outcome of this plot is just that I am fully entitled. It depends on the window of frequencies and observation times in which I would like to reproduce the result of theory, and I am fully entitled to take this approximation, but the only thing that f and times t should go up to pi n. So all above this value will give us meaningless results. Now, next point. If we make Monte Carlo simulations, then and record our trajectory at some discrete time moments, then appropriately discretizing this expression for the power spectral density of a single trajectory, we get a single trajectory periodogram, which will have this form just after discretizing, and using scaling properties of Brownian motion, we can cast, it will be equal in distribution to the following object here, and here it is just Poya random walk stepping on integers at integer moments of time. If we further rewrite it, reproducing a Poya random walk trajectory as a sum of increments plus minus 1, and we plug it here, we end up at the following representation of the periodogram of a single trajectory. So it is sum of squares of two squared sums where we have these increments, so these are coupled objects, and these are length, time-dependent length of random walks, which are sums of either cosines or sines. And so we have two coupled random walks with, in general, irrational and incommensurate length of step. Now, you may average to get the moment generating function. You may average this moment, and you can write it like the following integral. It is quite easy and straightforward. And inverting Laplace transform, you may get the following exact expression, formally exact expression for the full distribution function. Now we can look on different limits. For instance, we can fix frequency and observation time and go to the limit of an infinite number of points. And then usual analysis gives us the following result for the moment generating function, which is just our fellow, which we have seen on the previous slides, with accuracy of 1 over number of points. Now, question, if we do Monte Carlo, where to fit, in which region? Because now, as I said, we have a periodogram and behavior becomes periodic. So this is just for 10 points to get you an idea of what happens here. So red curve here, it is our first moment of the periodogram. It is dashed line, which goes like this. Green line, it is standard deviation. You see that they basically follow each other very, very closely, except for some points. You see it on the ratio of these two. This blue line gives us the coefficient of variation. You see that it basically hangs around square root of 5 over 2, but it has peaks at half periods and periods up to square root of 2. No, which means that we should fit somewhere here between the this epsilon which we defined and half a period here. Now you see the same on the level of the first moment. So here black line is the exact expression, and here what we get from taking the number of points 10 in power 3, which will be blue, and green one, it is 10 in power 4, and 10 in power 5, it is red. We see that we cannot go here because this is already a spurious behavior, which is just because we deal with a finite data set, but not a continuum. So we should fit somewhere here for the blue case, somewhere here for the green case, somewhere here for the red case. Now, how it looks actually in numerics, this single trajectory power spectral density. This one is for random walk. You see that basically these are, as I said, a set of lines which are shifted a little bit from each other by some random due to some random amplitude, but basically it is a slope 1 over f squared. So we can see from a single realization of Brownian motion 1 over f squared spectrum. And a second set of curves, it is corresponds to the truncated Wiener series. This is about single trajectory relations when I took a random variable divided by the first moment, and I said that in distribution it is the same as random number A. This we check here for one component, this is this curve, two components, and three components case. So you have a perfect agreement. And this is the function which defines in all the cases the distribution of random amplitudes A. This is how it looks in experiments. And experiments with a micrometer-sized bead just in water, which makes its usual Brownian motion. So these are sets of individual trajectories. This is slope 1 over f squared. And this is the corresponding distribution for one component case and two component cases. So it works perfectly well. Now, what I said you about which form of the distribution you get in the discrete case, when you fix frequency, fix time, and tend the number of points in your trajectory to infinity. Which one? They should not be on top of each other.
They are not identical particles.
Where? You mean here?
In the experimental data, you have lines parallel one to the other.
Yeah?
I thought the message is that
The slope.
the average should be the same, no? With some small fluctuations. No?
Yeah, but I don't take the average here. The average over 5 trajectories, it is this curve.
So the distribution is along frequencies or along...
You mean here? No, this is distribution for the value of the proportionality factor. Random amplitude.
One frequency or different frequencies?
For several different frequencies.
One molecule or for different...
For one molecule, 150 realizations of its
I
trajectories.
just want to understand, if you take a simulation of Brownian motion, and you do the power spectrum, and you repeat it 2 times, the lines will not fall very close to one on top of the other?
No. No, you have random proportionality factor, which has quite, I did not talk about this, the shapes of this function, but it is quite broad as well.
These are different frequencies, not global.
This is independent of the frequency. It is for frequencies much larger than 2 divided by pi epsilon. When you expect that there is no more any dependency on frequency except for that embodied in the first moment.
Really, what you showed is that the slope of is essentially the same for all the trajectories. So it's independent of the frequency what your amplitude scatter is. I think you have different diffusion also than different particles.
No, it's just one simple particle and 150 realizations of different trajectories of this very particle in this very water. Now, what I looked actually before, when I have shown you the limiting form of the distribution in the discrete case, I fixed ft and I let number of points to go to infinity. You may pose a different question when ft scales with m. So I'm sitting at something like 1/4 of the period or prime period or 1/2 of the prime period and let the number of points go to infinity. In this case, we cannot prove anything. Except that we can conjecture the form, and the form will be only different that here you will have a first moment of the periodogram. And what we can do, actually, we can prove this statement for several particular values of the frequencies. There are several magical values of the parameter f times delta, and delta, it is number of points divided by the prime period. Actually, when this ft, it is some prime number times, when a rational number, sorry, times pi m, and for which you can perform exactly averaging of the moment generating function of this functional. For instance, this is the case when it is either 0 to pi, so at the end of extremities of the prime periods, we have aj coefficient which enters here, which is a linearly decreasing function of the number of steps. Then you have other case when you are at the 1/2 of the period, you have at 1/4 of the period, you are at 2/3 of the prime period. In this case, the values for aj, bj, the jump length very much simplify, and you can carry out averaging exactly. So if someone is interested, so in our new Journal of Physics paper, it is discussed in pretty much detail. Now let me go to the fractional Brownian motion, which is a Gaussian process with zero mean and covariance function given here. What is here? It is called Hurst index, and it can take any value between from 0 to 1. For the case when you have h equal to 1/2, you have standard Brownian motion. For h bigger than 1/2, you have superdiffusion, you have positively correlated increments, and for h less than 1/2, you have subdiffusion and anti-persistence in consecutive values of the increments. So generalization of over d-dimensional cases is a little bit speculative. We again think that can be represented as a number of components, and these components are statistically independent. We don't have a better definition, but it suits us perfectly well. So, as for Brownian motion, where we used Wiener representation, it is very convenient here to use Japaridze-Van Santen series representation, which is a generalization of Wiener result, and then you can carry out all the calculations. In here you see that eigenfrequencies of the expansion are no longer multiples of pi. These are zeros of Bessel functions. Xn small is zero of Bessel function j minus h, and yn, which appears in cosines, it is a consecutive zero of Bessel function j1 minus h. Coefficients here are random Gaussian variables independent from each other, with the variance given here like combinations of such a form. You have zeros of Bessel functions and Bessel function corresponding to y component taken at 0 of the x component, and so on. Now, it's not surprising that you get for the moment generating function exactly the same equation that you got for Brownian motion, because basically you deal with the Gaussian process. This is what you expect. The only thing that, of course, first moment and coefficient variation will have a different form. About first moment I will talk a little bit later, but here I will show you some very surprising feature of the coefficient of variation. Here you see, now we plot several results for coefficient of variation as the function of omega, which is product of frequency times t. Oscillating curves are exact mathematical results corresponding to different values of h. Dashed lines go in here. It is square root of 2. This is square root of 5 over 2, and this is 1. And this is the asymptotic form. It is very difficult to see it here, so I plotted it a little bit bigger. This is asymptotic form, which is just average of each oscillating curve. And it's pretty simple, which is also surprising. Now what we see is a very strange thing, that this gamma gives you a clear-cut distinction between subdiffusive, superdiffusive, and Brownian motion. For Brownian motion, h equal to 1/2, we have that oscillations go to, gamma oscillates, but saturates at square root of 5 over 2. For superdiffusion, regardlessly of the value of h, when frequency goes to infinity, frequency times t goes to infinity, they all saturate at square root of 2. For subdiffusion, regardless of the value of subdiffusive h, they saturate at 1. And it is a pretty important thing, because you quite often see works where somebody says anomalous diffusion somewhere in the cells or whatsoever, the dynamical exponent is not 1 but 0.97. And just do it if you can create average. You don't even need to go to the limit of very long observation time. You just have to observe the trend. If it saturates here, it will be diffusion. If it is indeed subdiffusion, it will keep on going down. And this is a universal feature, and it will show up at the end of my talk when I will talk about Ornstein-Uhlenbeck processes, which are some ultimate case of subdiffusion. Now, of course, if you look here and you see that for super diffusion gamma saturates at square root of 2, so this becomes 0, the distribution will be even simpler. If gamma goes to 1, like in case of subdiffusion, it is even simpler because this becomes a full square. And that's it. So, this is just a case of zero frequency, which basically you look on the distribution of the area under the curve, FBM curve, and you can calculate it exactly, the full distribution. Now let me separately consider subdiffusive case and superdiffusive case. So, to ensure that gamma saturates at some constant value does not bring us any additional frequency dependence, we have to take values of ft bigger than certain epsilon. This is again this argument about epsilon accuracy up to infinity. In this case, we have the moment generation function produces us a gamma distribution with a shape parameter k. You have a single trajectory relation of this form. Now this is realization dependent power spectral density. This is first moment of it, and in distribution they're equal in distribution to this parameter a, which have now a very pretty simple form. This is gamma distribution. As for the mean value, when observation time is big, it attains the following form. And you see that, okay, CH is some numerical constant which we define, and here you have f in power 2h plus 1 for subdiffusive case. And it means that basically you can infer the value of h from a single trajectory, looking on the slope of the power spectrum. In the super diffusive case, it is a little slightly different. Again, moment generating function gives us a gamma distribution with a different shape parameter. You have a single trajectory relation which has the form, and now B has a slightly different distribution, but the behavior of the first moment is dramatically different. It no longer attains a stationary form as the function of observation time. It grows, it's aging. Second story, which is very important, that you have a superior universal feature that the frequency dependence is 1 over f squared, precisely like for Brownian motion. So if you do fix your observation time, you do experiments, you see 1 over f squared, you say, aha, it's Brownian motion. No, it doesn't guarantee that it's Brownian motion. It can be it can be super diffusion, and the thing you have to look, it is aging of the amplitude. Okay, so, okay, this is just numerics which fit perfectly well, so there is no point to discuss it. These are experimental studies also, I will not go deep into detail. And now let us look on a little bit different process, and we are with Satya currently at the stage of looking only getting expression for the first moment. It concerns fractional Brownian motion, which you interrupt and reset to the origin at some random moments of time with exponential distribution. So it evolves like this, and we wanted to look at the power spectral density in the standard sense, so on the first moment, in the sense of the previous part of my talk. So these are two results, most important results of our work. First one, it is covariance of the process with reset expressed via the covariance of the parental process without reset at two different time moments for a fairly general process. In some sense, it is generalization of what Martin was talking about this last renewal, first renewal equation, but this is for two-time property, and again, it is for a fairly general one. Using this covariance, of course, you can calculate straightforwardly the first moment of the power spectral density. It has a very funny form. It is a sum of two Lorentzian. One is usual Lorentzian, what we have for Einstein-Uhlenbeck process, and second is Lorentzian in power h. And the very fact that we have these two Lorentzians give us a very particular behavior of the first moment of the spectrum in the limit of very large frequencies. For instance, if you have subdiffusion, then you see that this term dominates in the large f limit, and you get 1 over f in power 2h plus 1, precisely what we had for fractional motion without the reset. For superdiffusion case, this is no longer the dominant term, but in the large frequency limit we have this deceptive 1 over f squared, which we also observed for the fractional Brownian motion without reset. And now the question comes, if we can have all these things what we did for fractional Brownian motion without a reset here, and to calculate the whole distribution function, basically we may expect also the self-averaging of the variance, because you generate copies. Of course they are correlated, but you generate more and more copies with time, and maybe they decouple. And last point of my talk, I think I have something like 5 minutes. Abhishek? 10 minutes. Okay, wonderful. That's largely enough. I will talk about Brownian generator. So let us look on the following trajectory, rho tau, which has two components, x tau, y tau, which obey these two Langevin-like equations, stochastically differential equations, where these are force exerted on x component, Fy is force exerted on y component. You have potential, which has a parabolic form like this. U is a coupling parameter between the component x and component y. In the case when u squared is less than 1, you have a steady state distribution. When u is larger than 1, the particle will travel, trajectory will travel to infinity. So this is the most interesting situation when u squared is less than 1. And finally, what you have here are bx and by are just trajectories of two Brownian motions, but which are characterized by different temperatures. And what I'm going to tell you, basically, it's not very important that it's Brownian motion. You can take any sort of Gaussian signal, you may take fractional Brownian motion, the model will be still exactly solved. But particular features will emerge. Now, this model is known for some time, and actually in 2007, Riemann and Fillinger noticed that in the steady state, you have a non-zero torque on average, so it means that this trajectory will be, on average, rotating around the minimum of the potential. The fact that this model has a distribution for u squared less than 1, st equal to infinity, was noticed already by Exartier and Pelletier in 1999, and there were plenty of other works, and we also contributed before. And there are also some experimental realizations which are shown in papers of Ciliberto. Now in our recent work this August with Cherasoli, Dotsenko and Rovdoni, we looked on the bias case, because previous work concentrated on unbiased case, and it is a natural thing. You have exactly solvable model, you add forces which do work on the generator, such that you can look on some sort of fluctuation relations, you can look on effective temperatures, and they appear pretty non-trivial. But here I will not talk about properties of the steady state, I just show you the figures. This is the shape of the distribution in case when Tx is 20, Ty is 1. This is a distribution in the case when Tx is 0, so x component is in dynamics is completely subordinated to y component. And Ty is 5. This, not nicely, but you see that they are closed orbits, and actually the trajectory circulates, so it is a vector field. Green is not good for showing. And in this case, when one of them leaves at 0 temperature, it circulates in the other direction. And this is a curl of the current. For instance, in the case when Tx is 20, Ty is 1, you have a maximum here with 2 dips alongside. In case when you have Tx equal to 0 and Ty equal to 5, just inverse relation, the maximum here becomes a dip, and here these two things turn into maximum. This is just to show you, without any pretension on understanding, that it is not still being linear, it is a non-trivial model. And for this non-trivial model, I would like to look now on the full distribution function of the power spectral density of individual trajectories of this rotator. Now, for the single component case, this is what we have. This is x component of the trajectory rho, and you end up at having the same result. The only thing, of course, that, in the limit of when t goes to infinity, so we talk about stationary state, this is much more complicated object as a function of the frequency, and it depends on both temperatures. Now, as I said that there is some similarity for this localized process and subdiffusive behavior for fractional Brownian motion, in the sense that we observe that coefficient variation tends to 1, like was subdiffusive case with h less than 1. So we have that standard deviation equals mean. It means that here we have 1, it becomes full square, and the distribution is pretty simple. It is a simple exponential, where scale is given by μx. So the whole argument I presented about single trajectory relation holds. In principle, for one very long trajectory, you can infer the spectral dependence specific to an ensemble. And to this end also, we may decouple these two equations, setting u0, and in this case, we deal with a simple Ornstein-Uhlenbeck process. So the full probability density function of the power spectral density of a single realization of Ornstein-Uhlenbeck process is just this simple result. Very complex, very simple, and apparently new. I have not seen it anywhere. Full distribution function. Okay, we talk. Now, two-component case. We create now the following object where we look on the two components. The moment generating function has this form, and the guy which appears here, it is Pearson correlation coefficient. It has the following explicit form here. And now, on the level of this guy, you may see that equilibrium and out of equilibrium, correlations in equilibrium and out of equilibriums are pretty different. So red curve here, it is behavior of correlation of the Pearson correlation of coefficient for Tx equal to T1. So when you don't have any rotations. You see that it vanishes very rapidly with the frequency, and namely it goes like 1 over frequency in power 4. This curve here corresponds to the case when Tx is not equal to 1. So when true non-equilibrium, we have rotations and so on. And in this case, Pearson correlation coefficient vanishes like 1 over f squared, much slower. And the prefactor here, amplitude, is the square difference of two temperatures. Last case, which is plotted here, it is the case when you have T0, Tx equal to 0, so x component leaves at 0 temperature. When y component comes, it a little bit perturbs it, then it goes away, it stays still, and so on. But dynamics of x component becomes, in this case, completely subordinated to the dynamics of y component. It is very natural that rho is identically equal to 1. So x component of the spectrum and y component are pretty strongly correlated. And last point is that we can invert and get the joint distribution function, which is again has a form of Bessel function. Here you have a square root of S1, S2, which is variables associated with Sx and Sy. And the interesting story about it is the shape of this distribution. For instance, you look on this distribution as the function of S1. The probability that Sx takes the value S1 at a fixed value of S1. So there is a gap of values of S2 in this case when the function of S1 is monotonic. As soon as you pass this threshold value and go to larger values of S2, it becomes non-monotonic. And this is the trace of correlations which emerge of the system in some strange way. And of course, when you go to the limit Tx goes to 0, such that rho is close to 1 and goes to 1, this function becomes a delta function, so they're rigidly correlated. So, I skip conclusions, and just let me finish by thanking you for your attention.
Okay, thanks for clarifying these distributions of the first part. But I have a question. I think what you should look, or maybe you already looked at, is the correlation between the spectrum at frequency 1 and the spectrum at frequency 2. Because the question is, along one power spectrum, will it be a global shift or will it be just a fluctuation along the average? In my opinion, this is major because what will happen, in my opinion, will that if you have two frequencies, eventually they'll become decorrelated one from another. And then you have this noise along the global line and you are just fluctuating around that curve for one single realization. So did you look at the correlation between two different frequencies along one line?
No, but it's a good suggestion. I can do it, yeah.
I'm telling you it will be decorrelated.
Hmm?
I think it will be decorrelated,
I think so,
that's
yeah.
why I don't understand the experiment, because the global lines, you should have lines and then random noise on each line. That's my guess, but maybe I'm wrong.
It's not me who did experiments.
Yeah,
so,
because you have different diffusion constants, and that's why you have the different.
The same. It is Diego who did the
in simulations.
Simulations.
Right.
Albert, I don't hear you.
I mean, in the simulations, you fix the constant and you see the same effect.
Yeah.
So there is no reason to expect that there is a fluctuation.
Where are the simulations?
These are for FBM. Huh? Oh, there are plenty of things. There are plenty of things. You vary. You look on the average over 10 realizations for the first moment obtained by averaging over just 10 realizations as a function of frequency. This is a function of frequency. You have different slopes. It should be for subdiffusion. For superdiffusion, you have the same slope regardless of the value of A. Ah, okay, that's a little bit earlier. Yeah. This is experiment. These are numerics.
You see that the curves fall one on top of the other. That's what I'm saying.
I'm not sure that.
On the right, you have the amplitude distribution that you get exactly from the simulation.
I'm not sure that this is. I'm not sure that they are on the line, on the same line. Yeah.
Fluctuations along the line, not between the lines. The two lines are falling one on top of the other. There's no global fluctuation.
This is logarithm. This is 0. Then this is 10 orders of magnitude, 20, 30, 40. On these scales, they seem to be on the same line, but these are all.
Sine and cosine move the same.
Yeah, absolutely. This again, you have from 0, you have from -8 till 8. You have plenty of orders of magnitude. They look to be on the same line, but in reality, of course, they are shifted. This is, you simply have a logarithmic scale.
Gleb, you mentioned that you suggest this technique to distinguish subdiffusive, superdiffusive behavior.
Yeah.
How long the trajectory do you need to make the distinction? So if it's like 1,000 points, 10,000 points.
You mean this point?
For fractional Brownian motion, when you look gamma, for gamma, and you say that this plot. Yeah, this one.
Maybe I put a wrong one because I had the same figure but with numerical data. Apparently I put a wrong one. I think that it was quite a lot. This was quite a lot, and for high frequencies specifically it was quite a lot, about 1,000 to reproduce gamma. But to reproduce our predictions for the distribution, not really. These are for agarose gel where you have subdiffusion. This is for telomeres in mammalian cells where you have subdiffusion. One component, two components. this is 150 realizations, and you have a perfect agreement between our prediction, theoretical curve, and experimental one for two different age. Yeah. A little bit not so good for two-component case with vacuoles, because we predict a monotonic curve for one-component case is perfect. Two-component case we have more like in the subdiffusive case with the maximum, but vacuoles is not a clear situation of superdiffusion because at the early times they're subdiffusive.
So to continue on this possibility of distinction between the different regimes, when you have a process that could switch between, let's say, two diffusion coefficient, D1 or D2, or just moving by diffusion, then you have drift.
Mm-hmm.
Then suppose we apply your statistical analysis, we should be able to see deviation
from normal Brownian.
From a normal Brownian
yes,
motion.
Definitely. But on transients. I don't think that maybe you will have in the leading behavior 1 over f squared, but some combination of diffusion coefficients.
That would be very interesting to see what to expect in deviations and what can be read from this deviation to extract parameters.
These are just two lines of calculations. Actually, it is not for two diffusion coefficient cases.
Yeah, for example, or for diffusion drift, and what kind of how to extract this. It would be very interesting to give this type of readout for people to do experiments and extract what they need.
Okay, I think we have run out of time, so let's thank Gleb and David.
Thank you once again.
So good morning. Well, first I will thank the organizers, Gregory and David, for inviting me and the center for hosting this conference. Today I will present some recent results realized with my PhD student, Yann Lanazoulet and Nicolas Moutal, about the first passage time in dynamic heterogeneous media. So during this conference we have heard a lot about the first passage phenomena. You can think on macroscopic scale about animals searching for hiding place, for food, for mates. Or at a microscopic scale, it's the main transport mechanism for most biochemical processes when some protein or enzyme has to find specific location on DNA chain to initiate the reaction. And this mean first passage time in mathematical terms, let me formulate in the following way. We have some Euclidean domain, and on the boundary of this domain there is a target. Target can be essentially anything. It can be a hole through which particle can escape from the domain. It can be a catalytic site, a protein, whatever. And there is a particle here in green which moves in the domain and search for this target. And we would like to know what is the first time when the particle comes to the target. So of course this problem depends, the distribution of the first passage time depends on many things. It depends on the target size, shape, location and type. It depends on the shape of the whole domain. It depends on the starting point location, and of course it depends on the type of the diffusion process. So again, in mathematical terms, we're interested in these quantities. So x of t is a given stochastic process, and we'd like to know what the first time when it arrives onto the subset of the boundary gamma. So this random variable is characterized by the probability density function or by the cumulative distribution, or equivalently, you can characterize it by the survival probability. So the probability that the particle has not found the target up to time t. And so for a normal Brownian motion, for the most standard and the most studied case, it's a well-known mixed boundary value problem. So you have the diffusion equation for this quantity, this diffusion coefficient, delta is the Laplace operator, with mixed boundary condition. So we impose Dirichlet boundary condition on the target, which means that if we start from the target, we are already on the target, so there is no way to escape, so the probability is 0. And on the rest of the boundary, there is no probability flux, so the particle cannot go through this boundary. And so the main essential difficulty in dealing with this problem is how to deal with this mixed boundary condition. And in fact, formally, you can relate the survival probability to the propagator. So the probability if you start at time 0 at point x naught to be at time t at point x without hitting the target. And again, formally, you can write down the spectral decomposition of the propagator in terms of the Laplace operator eigenfunctions. And again, you keep exactly the same boundary conditions. Why I say it's formal solution? Because essentially what we did, we reduced one complicated problem to another even more complicated problem, finding the eigenvalues. On the other hand, if you have simple domains like a sphere or a disk or an interval, this is exactly the way how this solution is obtained. So you can compute, in this case, Laplacian eigenfunctions, and then you get these standard spectral decompositions. What I like to say is that here I put the target here explicitly on the boundary, but it's from a mathematical point, you can also put the target inside the domain. Essentially, it changed nothing except that you just now have the boundary, which is has two components. One, this blue one reflecting, and the other one is red one, which is absorbing. So all this is true. And of course, you can also put many targets of different shapes. Exactly, it changed nothing from the mathematical point of view. And in addition, you can put a lot of obstacles inside. So in that case, you put just Neumann boundary conditions on the obstacles. And again, so you just make the boundary more and more complicated. So of course, in practical terms, when you try to compute, for instance, this probability, the survival probability, or the eigenfunctions, the problem becomes more and more complicated, but the formal solution is the same. And the idea is that once you try going to make the domain more and more complex, you may somehow approach to a more realistic situation, which would look something like that. So this is a picture from the paper by McGuffey in Ilcock, where they did a very accurate molecular dynamic simulation of many, many proteins. So each object here is some protein with its more or less realistic shape. And essentially, in this case, you can try looking at the problem. For instance, you consider some specific protein, and you'd like to know what's the first time when it arrives to some other point when there are a lot of obstacles on the way. Well, of course, in these descriptions, there are many limitations. In particular, this analysis assumes that the diffusing particle is point-like, and the protein is not. And of course, in practice, you have many interactions. But also, there is another point which is crucial, that all this analysis assumes that the boundary itself is fixed. And what you have in practice is something like that. Again, it comes from the same simulations. So all these proteins, they're moving. And so in that case, it would mean that all the obstacles in the picture, schematic picture I presented, would move. And of course, in that case, this approach is not, strictly speaking, appropriate to deal with the problem. So this is the motivation of the work. So how can one incorporate, at least effectively, the effect of this randomly ranging medium to this first passage time problem? And so the idea, well, is not new. So what one can use is the concept of the diffusing diffusivity. So let me go back again to the stochastic equation, first in homogeneous case. So here you can write, well, the most simple stochastic equation for free Brownian motion. And here what you have, dWt, is the white noise or the increments of the standard Wiener process. So they model somehow the interaction of the particle with the surrounding medium. So it's thermal fluctuations. And in addition, you just to put the intensity of these interactions as a diffusion coefficient. And so, for instance, if you have higher temperature, you would expect higher diffusivity, so the particle moves faster. Now, the situation in the rapidly ranging medium is different because the particle moves, but the medium itself, it changes. And so you can expect that in some places, the intensity of interaction is high, in some places it's lower. And so the natural idea comes that, okay, let's now look on this intensity as a stochastic process itself. And so in this way, we try to account, again, effectively for the medium rearrangements. So let me give you an illustration. So suppose this is our target. This is a particle which is moving. And then, so here's homogeneous case. And here, so it moves according to this equation. There are thermal fluctuations, some local shocks, which make this zigzag trajectory, which is the direction of Brownian motion. And then at some point, it comes to the target. Now, we would like to deal with a more complicated situation. You have a medium, which you can think about this as actin filaments. Then the particles move inside. And again, along its way, it would encounter different local densities of particles, so it will feel different interactions. And so the idea is that now, for instance, this is a snapshot picture of the medium arrangement at that time when the particle starts, and here is a snapshot of the medium at a later time when the particle is on its way. So the medium could completely change in this case. And so the idea now that we try to count these changes by introducing this stochastic diffusivity or diffusing diffusivity. And so, for instance, these blue values would mean that particles move to the denser region, so it's more slower to explore the trajectory, the medium, and red corresponds to more looser regions when it's much faster. And so in that case, and the crucial point here is that somehow we decouple thermal fluctuations, which essentially remain the same, with the fluctuations of the medium. And again, I'm not going into details. It's essentially you have time scale separations, interactions when the particle is a solvent, which is essentially water, and the rearrangement of the medium itself. And so in that case, the thermal fluctuation will still determine the trajectories, so the statistics of trajectories, but these trajectories would be explored at a different speed. Well, I put speed in quarters because it's not very well defined for Brownian trajectory, but at least you can think about it as exploration, the rate of exploration of the trajectory. So again, here it would represent denser region, here it would represent looser region, so fast exploration of the same trajectory. Okay, well, next comes the point how to choose a model for the diffusing diffusivity. And well, one of the first at least I know, it was proposed by Trubitsky and Slater, who actually coined the term diffusing diffusivity. So they just used the reflected Brownian motion on interval. So the main constraint here you have to impose that the diffusivity is non-negative, right? So and this is why you cannot just put Brownian motion, because it can become negative, so here you put reflected Brownian motion. Somehow, physical inconvenience of this choice, it would mean that the diffusivity would essentially more or less uniformly sample all possible values, say from 0 to some maximal value. And so I would say that somewhat more physically justified choice was done in next works when the diffusivity was modeled as the kind of Einstein-Beck process. So we have some mean value around which the diffusivity fluctuates. But again, to ensure that it's positive or non-negative, you take the square of this process. And if you have introduced some extra parameter freedom to your motion, in fact, you consider the collection of n independent Einstein-Beck processes or n-dimensional Einstein-Beck process. So it's a way to model that. So in a recent work with my students, we proposed to model diffusivity with the Feller process, also known as the square root process, or in financial literature as the Cox-Ingerson-Ross process. And in general, you can take essentially any stochastic equation you like, and just you have to again ensure that the diffusivity is non-negative. So in particular, this Feller process corresponds to the particular choice of the drift term for diffusivity and diffusivity of diffusivity in this way. So if you substitute it here, what you get is this Feller process. It looks like the Einstein-Beck process, except that there is extra term here, which is proportional to the square root of diffusivity. And this term automatically ensures you that diffusivity is non-negative. So the solution of the stochastic process is non-negative. And so this model has essentially just three parameters. So it's mean diffusivity, so the mean value around which the diffusivity would fluctuate, the mean reverting time, so how fast it would return to the mean value, and intensity of fluctuations of the diffusivity. Right? So in this talk, I will stick to this particular model, but in fact, many results I will present can be generalized to essentially any stochastic model you would like for your diffusivity process. Okay, so first of all, as I said, you have three different parameters, but let's try to identify is there some key parameter which would essentially determine the properties. And to do that, what you can do, you can rescale this equation by dividing the diffusivity by the mean diffusivity and time by tau. So in that case, you get some equation which is completely dimensionless, and you have only one parameter, which is essential here, which would determine the amplitude of fluctuations. And so it's natural to introduce, well, this control parameter, which would be diffusivity divided by tau sigma square. It's dimensionless, and in that case, it appears that the square root of 1 over nu. And so let me mention that this Feller process, it's a natural generalization of the former work, because if you take nu, this parameter is integer, then the Feller process is fully equivalent to the square of n-dimensional Einstein-Lebesgue process used in previous works. But here it's a generalization to any value of nu, and it's not just switch from integer values to real values. The advantage here is that if you take nu, which is integer, then the disorder strength, it would be always bounded by 1. So in fact, with this Einstein-Lebesgue process, you cannot go to strong disorder in the system or strong fluctuations of the medium. And so now in this way, you can go explore all kinds of disorder in a continuous way. As you will see, it will change significantly the properties. Okay, let's focus on the properties of this model first. And I'm not going into the detailed analysis of these properties. I will essentially speak about non-Gaussian property of this diffusion. So for this set of coupled stochastic Langevin equations, you can write down explicitly the Fourier, the Fokker-Planck equation, and then you can essentially solve it exactly. That is done in this paper. And you find a solution in the form of the Fourier transform, inverse Fourier transform of a completely explicit function. Well, this function may be not nice looking, but it's fully explicit, while omega is just intermediate auxiliary parameter to make it a little bit shorter. And essentially what is important here, that you can recognize nu, again, the disorder strength. Yes?
So this is you are interpreting the Ito or something?
Ito. So, sorry, I didn't specify, but yeah, it's in Ito sense. So here, in particular, if you take the disorder strength 1 when u goes to 0, so when u goes to infinity, it's easy to check that this function goes to just exponential function, and in that case, you put it here in the Fourier transform, and you get your Gaussian propagator. So naturally, when you remove the disorder, you come back to just homogeneous diffusion. However, whenever the disorder is present, you would get non-Gaussian diffusion, and so non-Gaussian distribution of increments. So in particular, one can show that the large distance behavior of the propagator has this form. So you have exponential decay with some explicitly computed function f of t and some power law correction. So you have due to disorder, you change from the Gaussian behavior to this exponential decay. And so just to illustrate it here, this is one particular example. So at different times, so at smaller times, you have your propagator, which is narrower. And so you can clearly see in the some logarithmic plot that it's straight lines, so it's exponential tails. And when times go on, this distribution becomes smoother, so it recovers this parabolic shape in the middle, but then still you have tails which are exponential. And naturally, it's very long time, this smooth and Gaussian-like behavior would dominate, and you have to go to extremely small probabilities to find out the exponential tail. So, sorry? Oh, f of t, I do not provide it. It's explicitly computed function. It depends on time.
How does it look like?
Oh. Well, it involves a solution of some trigonometric equation. So, I mean, it's not kind of very simple function. So, again, for Gaussian case, you would have square here and 1 over t, so it would be very simple. But in this case, it's not so simple, but it's fully explicit.
For large time,
and you have all asymptotics of this function. So for large time, the propagator kind of in this region, it becomes closer to the Gaussian. So at long time, you have a transition to the Gaussian regime. In particular, what you can compute, it was computed that you can compute non-Gaussian parameter, which is essentially this fourth moment divided by the square of the second moment, and you can see that it goes to 0 as 1 over t, essentially. Well, with some.
And at very short time, is there a chance that you remember?
Sorry, at very short time?
At short times, f of t, how does it look?
We can discuss. I will check. Okay. So, but this is this property. Okay. Now let's move to the main topic of this talk. It's about the first passage times. So, because before all the study was on just free space. It was just about the dynamics itself. Now we start to consider the simplest possible case. It's one-dimensional diffusion, and you put just one obstacle, for instance, in 0. Oh, obstacle, target, I'm sorry. You put just one target here. The good point here with this target is that you don't need to modify the stochastic equation itself. You just stop the process when you arrive to the target. And that allows you to, again, to write the Fokker-Planck equation. But in fact, in this particular case, you don't need it. Because essentially, you have your propagator on the whole line, and then you use just the method of images. So you put some fictitious source on the other side, and then you take the difference between two propagator. That would ensure you that the Dirichlet boundary condition is satisfied here. And in this way, you get the propagator. And from the propagator, you compute the survival probability and the probability density function, taking the derivative of that. So all these three, it's essentially differently written Fourier transform of this explicitly known function. So let me show how it looks like, the distribution of the first passage time in one-dimensional case on the half line. So the gray curve is the standard solution for homogeneous diffusion, given here. And the blue one is the solution for heterogeneous one. Just for some choice of parameters, it doesn't matter here. So you can see first that at long times, the solution, again, you have exact explicit solution. So you can write down all the asymptotics you like. In particular, you can check that it goes as t to the power to 3/2. So it goes closer and closer to the homogeneous diffusion, and that's natural. In long time, particle has enough time to average out all heterogeneities of diffusivity, and then it moves and diffuses like just homogeneous diffusion. On the other hand, you find a completely different behavior at short times. And again, it's somehow expected. So you can see this is asymptotic behavior. So you have exponential term here and some power law correction. But what is crucial that if you look on this exponential, it looks like a square root of this term with some extra factor here, nu. So in fact, it means that in the short time limit, this parameter is large, and so the decay of this left tail is much slower than for homogeneous case. And physical explanation is quite simple because you sample different diffusivities in some sense, and the fact that you allow some diffusivity to be above the mean one would essentially dominate on the overall statistics, and that would make this tail much higher. But it means in practice that it will facilitate arrival to the target. Well, with some extra effort, you can also solve the exterior problem for the sphere, and again, you get the solution. Well, I skipped the details, but this is just the density. And again, essentially, it's related to the image method, so you have to ensure that the propagator is on the boundary of the sphere is 0. And from this probability density function, if you assume that there are many particles distributed uniformly in the bulk, then you can just integrate it, and you get the macroscopic reaction rate coefficient. And of course, you can recognize that this Lomonosovsky rate that what you get for homogeneous diffusion, but the approach to this stationary steady-state case would be different. It would be affected by the disorder. And this is the solution by Smolykovsky 1 century ago, which is just 1 over the square root of t.
Did you describe the short time asymptotics?
Yes, you can get everything. Again, you have explicit form for here, so you can obtain all the asymptotics. Okay, so now let me go back to the main topic. So now that was 2 examples where we use the symmetry, particular symmetry, and there were exterior problems. Now let me come back to the interior problem. So first passage time in a confined domain. Well, first of all, I would notice that again here we have many obstacles, but all these obstacles now considered as moving, so they're already taken into account by diffusivity, so I can remove them. But still now you have the outer boundary, which is supposed to be fixed. And that's of course a problem as compared to the targets, because now when a particle comes to this boundary, the process is not stopped, but it has to be pulled back, and so the particle cannot go outside. And so here there is no way to remain with the same equation. You have to modify the stochastic equation itself. Well, fortunately, it's quite standard procedure. You have to add some extra term here. Here n is the unit vector directed towards the domain. So 1 is the characteristic function on the boundary. So this term is only non-zero when the particle is on the boundary. And finally, the most kind of difficult part is this DLT. LT is the local time of the process on the boundary. And this is a well-known Scuola equation. And there is something mysterious point, at least for me as a physicist, that this single stochastic equation simultaneously determines the process itself and the local time process. So for those who know this effect, it's classical. For those who doesn't know, it's quite subtle, so I do not go into detail. The good point that for this set of equations, then you can write down again the Fokker-Planck equation, and then you can solve it. And in fact, you can get this spectral decomposition. And the only difference with the spectral decomposition I presented before is just that the exponential functions here are replaced again by this upsilon function, which is determined by the disorder. So essentially, the eigenfunctions of the Laplacian in this domain would determine the geometry of this bound confinement and the reactivity of these targets. So where are they located, what is their shape, etc. And in terms of the dynamic disorder, it enters only in this part. And again, if the disorder is removed, then you get this exponential term and you recover the standard spectral decomposition. Sorry? N of xt, it's a normal vector directed inside the domain. So essentially, this term tells you that whenever a particle comes to the boundary, it's pulled back in the boundary. That's kind of physics intuition explanation for that. Okay, so then again, from this expansion, again, it's formal because then you have to put inside the eigenfunctions of a given confinement. You can derive this Ralf probability and the first passage time density. It looks like that. So let's look in more detail in this quantity in particular. It's long time and short time behavior. So long time is much simpler as usual because you know that the Laplacian eigenvalues are non-negative increasing sequence of eigenvalues, and so at long times the smallest eigenvalue would determine the asymptotic behavior. And so in this infinite sum, there would be one term which would provide the main long-time asymptotic behavior. And this term would look like that. So I just put the dependence on time here. So what you can see, you can recover again the terms that you would expect just for homogeneous diffusion. So the mean diffusivity T and the smallest eigenvalue. But this term is this factor is corrected by some reduction factor. So it's reduced by some coefficient. And what do we see in this coefficient? So essentially it depends on these parameters. First, if you take the smallest eigenvalue to the power of 1 over square root, then it would give you the largest length scale of your problem, geometric length scale of the problem. On the other hand, this product, it's homogeneous to a length and can be interpreted as a disorder length scale. So that's the parameter of the rearrangements. And so we can look on two different asymptotic cases. When the disorder length scale is much shorter than the geometric length scale, then naturally this factor is close to 1. And again, the particle has enough time when it goes to the target to average out diffusivities. And so you get this average result just for homogeneous diffusion. On the other hand, if the disorder length scale is much larger than the geometric scale of the problem, then this factor is essentially dominated by this ratio and it's significantly reduced. So it means that in that case, heterogeneity remains strong even in the long time limit. And what is important is the right tail is significantly increased. And the right tail typically is what would determine the mean first passage time. And so it means that the mean first passage time would be again increased essentially by this factor. So on average, the disorder would slow down the dynamics. That's what you naturally would expect, that it's much easier to go in homogeneous case than in heterogeneous one. Now let's go to the short time behavior. As usual, short time behavior is more complicated because it involves all the terms, so you cannot make truncation. I skip technical details, but you can still write down all these asymptotics. And no surprise that for the first passage time density, you get exactly the same asymptotics as just for one-dimensional case I presented. Here, again, what matters is the distance from the starting point to the closest point on the target. And so this is essentially this distance what you get. And again, you get the same kind of 1 over the square root of t dependence in the exponential. And again, you can see that heterogeneity drastically changed the short time behavior. Here's again the asymptotics for the homogeneous case. So this factor is large. So here the left tail is significantly increased. And moreover, you can see that the stronger disorder, so it means the smaller new parameter, would facilitate the arrival. So it's essentially, it controls the amplitude here. So the arrival would be faster. So let me give you, so these are just general asymptotic behavior. So let me give you just an example. And I will take the simplest example possible, just a sphere. We start in the center. And what is the time to arrive onto the boundary of the sphere? The advantage of this example is that everything is computable explicitly. And the first passage time density, it looks very explicit. It's just a series. And again, epsilon function is explicitly known. It's exactly the same as before. So what I will do, I will fix 2 parameters, which essentially length and time scales, and I will explore the space of 2 other parameters, which are essentially the disorder strength and the disorder scale. And the disorder scale, I will renormalize it by R to get just dimensionless quantity. So it will be analysis in this space of 2 parameters. Let me start with the short disorder scale. So and here are the results. So here's the probability density function, the function of time, log scale. And black curve, it's homogeneous diffusion. So again, as we saw in asymptotic analysis, at long times, all the distributions are essentially the same and they're close to the homogeneous one. So here I didn't mention that here we change by color the different disorder strengths. So blue, it means low disorder strengths. Red, it means high disorder strengths. So in fact, in this region, it doesn't matter what the disorder is. But on the other hand, it significantly changed the distribution on the left tail. The situation became more interesting at longer scale disorder. So mu is equal to 10 here. And here you can see that not only left tail is affected, but also the right tail is affected. And moreover, you can also notice that the most probable value moves again to shorter times. So disorder, if you introduce stronger disorder, it would facilitate the arrival. Okay, so let me conclude, make the conclusions of this work. So in this model, we propose the rapid rearrangements of the dynamic heterogeneous medium are incorporated via diffusing diffusivity, and we suggested to model the Feller process. The diffusing diffusivity leads to non-Gaussian increments. I think it's an important point because in many experiments done in complex systems, in particular inside cells, the non-Gaussian features appear, and in particular this exponential decay with the distance appear quite often. The second part of the work was essentially to couple these non-Gaussian dynamics to the chemical reactions. And again, well, these were just diffusion-limited reactions with a perfect reactivity. Once a particle arrives on the target, it immediately reacts. And solving the Fokker-Planck equation, we obtained these spectral decompositions for the propagator, the survival probability density function, etc. We analyzed the short and long time behavior of the first passage time density, and we showed that the disorder would increase both left and right tails. As I said, we'll focus on this particular model for the diffusivity, but in fact, the derivation, in particular the spectral decompositions, they're general for other models. In fact, I didn't present in detail, but for the propagator itself, you can use just subordination approach, and in this way, you can incorporate any model of your diffusing diffusivity with this analysis just with this function epsilon. So it would just take another form of this function, but all the form of the spectral decompositions would be exactly the same. Of course, the short time, long time behaviors can be different, and that would depend on the choice of your model of diffusing diffusivity. And maybe the last conclusion, which is maybe more practical, is that, in fact, as I said, the disorder, on average, it would slow down the dynamics. So the mean first passage time would be slowed down and can be slowed down by 10, by factor, which is just not close to 1, but it can be 10 or even more. On the other hand, the fact that you have the left tail which is increased, it makes that the disorder can be beneficial for faster search and realization of an individual reaction event by a single molecule. So in fact, this disorder helps you some realizations which can be beneficial to a faster realization of your process. To some extent, you can see that the distribution becomes wider, and so in the wider distribution with the most probable value which is shifted to the shorter times. Now, this work is, of course, it doesn't solve all problems, and in fact, there are many perspectives that I see for this work. First of all, that I already mentioned that in this work we focused on perfect reactions. And in any experimental situation, reactions are not perfect. If you search for the first passage time to exit the domain, the particle has to overcome some entropic barrier. If you have some reactions, the particle has to overcome some activation barrier. So it means that when a particle arrives to the target, it has a chances to react immediately, but it has a chances to stay around and then leave the domain, and then it has to come back and come back again. So this effect was known for more than half a century, and there was a standard extension for these partial reactive targets, which proposed by Kimball in 49, is to replace the Dirichlet boundary condition on the target by the Robin boundary condition. So this condition essentially states that on the target, the diffusive flux of particles toward the target is equal to some chemical flux of the particle, so chemical reaction on the particle, and here kappa is the reactivity of the target. So naturally, then you can integrate and implement it, and you will see that the effect in some cases can be dramatic of this reactivity. But if you'd like to use this equation in this diffusing diffusivity context, you realize immediately that you even cannot write it explicitly because diffusivity is a random variable. So this equation doesn't make sense if you write it only for this marginal propagator. So what you can do, you can look on the full propagator. So you consider the Fokker-Planck equation in the space of diffusivity and position. And in that case, definitely you can write this equation. The problem is that once you do that, the way of solution of the Fokker-Planck equation that we used, it doesn't work. So one needs to go to other methods. Well, one of the technical problems that we use the Laplace transform with respect to D, and in that case you get some convolution here. So well, it's not easy, but I think it would be very important to do in future. Another important point, I already mentioned that if you have many particles, then you have to account for all for the contribution of different particles. The standard way to deal with that, if you say that the particles are small and non-interacting, then essentially you compute the statistics for a single particle. That was David, for instance, presented in his talk. And then just by very simple the independence, you get information for n particles. So in that sense, the problem is exactly reduced to a single particle problem. In this case, you can try to do the same thing. And in particular, since each particle explores the space its own way, then you can say that diffusivity would be also some stochastic processes which are independent. However, when the particles come close to each other, physically it means that the diffusivity, they probe the same environment. So the diffusivity starts to be correlated when the particles are close to each other. And so even if you assume that the particles themselves, they are independent, they still some coupled. Well, I expect they would be weakly coupled via this diffusivity stochastic process. So how to deal with this problem, I have no idea. Well, a somewhat straightforward extension is to look on the effect of the complex shape confinement to see how it would affect, how it would couple with the dynamic disorder. But it essentially requires the computation of eigenfunctions in some more complex problems. An inconvenient point of this approach that I assume that all obstacles are rapidly moving, but the target remains fixed. Well, if the target is located on the cell, say, cell membrane, that could be justified because, again, on the time scales, you can say that the membrane would move slower than the proteins. But if it's just a protein inside the cell, well, there is no reason to say that the target is fixed. And so I think it would be very interesting to see how can one extend this problem to mobile target particle. Well, coming back to the problem of the choice of the model, I think, well, in this way, it was just modeling this dynamic media model which comes from nowhere, essentially. It's just an idea that maybe it can capture some effects. But the question of how to select an appropriate model. And I think it would be nice to compare this result to brute force molecular dynamic simulations and see if they can help to select the model. And in the same way, I think it would be important to develop some statistical tools for the model selection and calibration of model parameters coming from the single particle tracking experiments. And again, I have, for the moment, no idea how to do that. But essentially, the idea is that we can use the knowledge of the propagator and the statistical first passage time, and then try to transform this knowledge into some estimators that can be used. But this is for future. Okay, well, that's all, and thank you very much for your attention.
Well, thank you. Thank you, Denis. So, just time for questions.
The solution you give, one of the limit is the free diffusion, right? Like
Sorry?
The tau going to 0 limit should give me the fixed diffusion constant problem.
Yes, definitely.
Yeah, but then the solution you wrote down, which is exponential of minus mod x minus x naught times f of t.
Yes.
Is it easy to see that that goes to the Gaussian distribution?
Yes, you can check that. Well, I only focused on this new parameter, which is kind of the main, well, from my point of view, the most important one. And then you can check when the nu goes to infinity, so when nu goes to 0, then you recover exponential. But you also recover exponential if you say sigma goes to 0, or when your tau goes to 0 as well. So when recover it, when the particle goes back immediately to the mean level. So essentially, it, again, and in this way, and the function is completely explicit, so you can just look how it works.
So that solution you wrote down is just a limiting solution, because their x part just comes out explicitly, right? And it's just mod x minus x0. So I don't see how it will go to a square of...
this is the story of non-exchangeable limits.
Okay.
So somehow, in one case, you look on the you fix everything and you go the distance large, and that gives you this exponential term.
Okay.
And if you do it otherwise, you get another limit.
Okay.
Definitely, definitely.
Yeah.
Oh, you choose a failure process? No, why the failure process?
Well, it was...
Because you can solve.
That's right. I would say that we came across the Feller process because it was already used in financial literature to study stochastic volatility models. And so essentially the process known to introduce, to get this positive process. And on the second, there is a kind of another motivation, not only to be able to solve it, that for the Feller process, it has stationary distribution, which is a gamma distribution. And from experimental work with our colleagues in Germany, Doris Heinrich, in experiment in cells, we saw that the diffusivity somehow that we measure looks like or can be interpreted in terms of the gamma distribution. So that was the motivation how to, kind of in a complex real medium, how to get to this diffusivity.
Probably there is infinite diffusion which have gamma distribution for the variant.
Sure, and that essentially is this point. So I have I'm not claiming that the Feller process is the choice to use. It is one possible choice which gives quite reasonable and experimentally observed effects, but maybe you can cook up other models which give you a pre-described distribution of diffusivity, and in that case you can use this particular model. Yes. Yes.
And then you have a kind of spectral decomposition, and you are able to access to the spectrum of the generator?
Well, in fact, let me try first to answer in a more simpler way. The fact that we managed to solve it from a physical point of view, that we assume that the diffusivity and the thermal fluctuations, they are independent. Yeah, and this independence, it also gives you some specific structure of the Fokker-Planck equation, which allows you again to decouple these two terms.
Yeah, but in general, the one-dimensional case, it's always available by shorter variable, but the two-dimensional case, it's very, very, very uncommon. And you can find a shorter variable while you find a spectrum. A generator which have no spectrum. It's very not famous. So my question was, how you solve this spectrum?
I would say
Denis, can
no.
I repeat the questions? Because here we don't hear what is asked.
The question is that in one-dimensional case, one can separate kind of two variables, and in that case, well, everything is okay. From high-dimensional case, it's not always possible, and in that case, what? Sorry? Well, here it's variables with the position and diffusivity, and if diffusivity and if position is not one-dimensional process but two-dimensional, three-dimensional process, then it could be more tricky. And what about the spectrum of the Fokker-Planck operator associated to this problem? So again, I would say that in this case, it's possible to do.
Yeah, but this is a class of models in which they are separated, and they are all solvable, independent of the dimension.
Yeah. Thanks, Ari.
In general, you can do separate and evaluate the model.
No, in this class of models, not in general.
Yeah, but my question is, this class of models is not about what university. Can you come back on the
So maybe we need this for a private discussion.
Yeah, I would be glad to discuss, because again, for me, I discovered this field, so, and of course there are many questions left, so I would be glad to discuss. Okay.
So just one final comment. Actually, a cell is quite diluted, and what is the most important obstacles are the organelles themselves, not molecules. The molecules do not create that crowding, but organelles do, like endoplasmic reticulum, vesicles. So, I mean, molecule by themselves creating this effect of local fluctuation of diffusion might not be necessarily the most important effect. The most important effect are the obstacle generated by these organelles, and the time scale of which are usually much longer. I mean, they evolve much slower than any molecules. So maybe for interior of the cell, maybe this, I'm provocating a bit, but maybe this theory might not be that relevant. However, if you are thinking about what you have on membranes where everything is crowded, maybe there could be some relevance, and might be interesting in the future to try to connect what you have done if you have, let's say, this universal type behavior model by adding by your stochastic equation for the diffusion coefficient, trying to extract something.
Yeah, thank you. It's a good idea, and just a short answer that, in fact, I agree with that. But also, you have a strong impact of cytoskeleton. In particular, well, again, from this experimental group, there are these movies where microtubules moving, and they perturb the medium, and so again, they can rescale or rearrange the whole dynamics. So, but it's open problem, open question, of course.
Okay, I think it's time to thank Denis again and move on to the next speaker.
Okay, do you all hear me? Very good. I always start with a beautiful image. I always start with a Turner. And this, for those of you who know Turner, it is a real Turner, it doesn't look like it. So this is on the road between Florence and Pisa. So that was my choice for this talk. It's a beautiful location. I've enjoyed the food here, the cityscape, which is beautiful, the churches. So thanks to the organizers for bringing us here. I'm very glad. Some of the questions that were brought up in the morning may be addressed during this talk. And the main topic is how do we treat systems where we have only one individual time series, can be long, and how do we deal with that with theories that typically provide us with ensemble averages. So what I want to convince you about is benign systems where we can more or less lean back and use ensemble theories. But there's other systems that are less benign where we have diverging time series or other kinds of divergences. And we actually have to come up with the corresponding time averages of the physical observables. Here you have one very simple example. This was done in a group of Ralf Engbert at my university. This is just eye movement of individual patients. They have to stare at one point on a screen, and then we have mean square displacements, we have correlation functions, and they're all time averages. How do we deal with something like that? So in this case, for instance, we found that if we look at these correlation functions, we see these very characteristic oscillations, and they give a clue to the psychologists at which level on the brain all the eye movement is actually controlled. There's another example, financial time series. Try to get an ensemble of a financial time series. It's not possible. So you have this one very long time series. Typically, this is the way how they're represented. So you have the value on a logarithmic scale. You have the time axis, and it's a more or less an exponential growth that's typically modeled by by geometric Brownian motion, which is multiplicative in the amplitude. So that's in a way similar to the model that Denis was showing us. And in this case, for instance, where you have to use time averages if you want to analyze the data. And in this case, the time average, for instance, it transforms the logarithmic growth into a linear growth, so you don't have to take a logarithm of your data. Could be of an advantage, and especially when we use some kind of analysis, I don't want to go into details, which you call a delay time analysis, we can even find some universality. So we go from this huge salad mess down to curves like that and actually find some common behaviors. So at least this is kind of convincing to me that time averages are interesting to look at. Now, a few years ago, we were talking about Einstein year and whatever. No one actually cares that we have exactly 190 years after Robert Brown's paper. And in this paper, he showed us that, Brownian motion, random motion, exists. And one of his, being a botanist, a grumpy-looking one, he actually analyzed that these pollen granules that he observed jittering around are no animalcules. I mean, one of the biggest questions was, is this stuff alive? Is it moving by itself? And he actually then had a whole series of experiments proving that it's a physical process, not a biological process. And I quote here, it's beautiful, rocks of all ages, including those in which organic remains have never been found, yielded the molecules in abundance. Molecules, that's what he called these fuzzing particles. And so he crushed all the rocks he had, and he still observed this jittering motion. Their existence was ascertained in each of the constituent molecules of granite, a fragment of the Sphinx. No terrorists needed destroying things. Physicists or biologists can do it. It's a beautiful paper. Read it. 190 years. You can read it on your flight back. It's a joy. It's also exactly 110 years. So it's a miraculous year. I mean, okay, it's not exactly 100 or 200, but we're getting close. After all these beautiful experiments by Jean Perrin in Paris, and I just recently found it's a new addition to the internet. It's the first time I saw him with his experiment in the Paris lab. And I've showed these images many times. These are trajectories. He measured small pieces of putty that he put in a water solution, and the trajectories were too short. So what he did is he combined many trajectories, and each of these straight lines corresponding to an excursion of 30 seconds per particle, he shifted to a common origin and just fitted the Gaussian solution to this displacement distribution. And then by using the Einstein-Smoluchowski relation, relating some microscopic quantity, the diffusion coefficient that you get from this fit, with Avogadro's number, here we have the gas constant and the other quantities, he was able to deduce Avogadro's number in the quest of discovering, atoms, right, the atomistic theory of matter. But the problem was the particles were not very identical. They didn't have means to create them. Even now when experimentalists buy these little plastic beads, these micron-sized beads, they have huge size distributions, whatever. So it was actually another guy, and I finally made sure that it's 100% the picture of the guy. Over years I've been walking around giving talks, and I was almost sure, but now I'm 100% sure. So this is Ivan Nordlund. And he was at the University of Uppsala. I quoted something in Swedish down here. And he was a wizard of photography. He was part of all kinds of expeditions to the north of Sweden, and he portrayed situations in the lab, but he was good enough in photography to invent a completely new setup. And the heart of the setup is actually here. You have a little motor that's driving the photographic film plate. So he used a moving film plate to actually create a time series of the motion. So you had a very small capsule, there was a water or some other liquid, and there was a mercury droplet, and you see the deterministic part, that's the sedimentation of the droplet. And then superimposed to it, you have the Brownian motion. And he used then the analysis of individual time series to determine Avogadro's number through the diffusion coefficient from individual time series, and only afterwards he averaged over the individual experiments, and his result for Avogadro's number, if you can't read it, it's much better than Perrin's. So this idea of moving from an ensemble average to a time average was very, very original and pushed the field forward. Okay, how can we understand this from a more statistical point of view? So typically when we think about the mean square displacement of a particle, we have in mind that we just average r squared over the propagator of the process. And here time is just a parameter, we have a spatial average, and if it's Brownian motion in d dimensions, that's what we get. When you ask an experimentalist what do they do with their time series, it's not a unique definition, but typically what they use, you have a time series that goes from time 0 to some measurement time capital T. Then they define the time average, and time averages are symbolized by this overline. It's a time average considering the displacement during a so-called lag time delta. You square it, and you average this over your entire time series. You normalize a little bit. When delta is very small and t is very big, it looks like our typical StatMech average, where it's 1 over t integral 0 to t. Okay? But by using this kind of average, you will see this is quite convenient for free motion. Now, let us look at what happens during this interval delta with a displacement that we square. If we have a random walk picture to it, on average, it means that the distance squared will be proportional to the distance squared of an individual jump. If you think of a lattice model, that would be lattice constant squared, or you have a jump length distribution, it's the variance of it. And then we just need the number of jumps, and the number of jumps is the lag time delta divided by the individual time of a single jump. Okay, that's just a random walk. So if we go to a long time limit, and we know that Brownian motion itself averaging, and then we just plug this into the definition, we get exactly this result. So that's exactly the ensemble average. We just replaced time t by the lag time here, and I identified the diffusion coefficient just by the typical random walk picture. Okay, so this is something that I want to call ergodic. The long time limit of my time average is exactly the same information as the ensemble average. Okay, good. Now we can go to these benign systems. We already heard a few of the terms, and let me quickly define what it means. The physical process behind this, you could imagine, for instance, as these Rouse chains that we heard of yesterday on Monday. So you can essentially write down the dynamic equations of motions for each of these particles. And of course, they're coupled by the springs, so they have nearest neighbor coupling. So you get a set of coupled Markovian equations. And you know that when you have even, let's say, a harmonic oscillator, you write down the stochastic equation for x for x and for the momentum. You integrate out momentum, plug it into the x equation. Already you have a memory. It's no longer a Markovian equation. And here even worse things happen when you integrate out all the other degrees of freedom, but the one coordinate that you're interested in, then you actually end up with this, what I call a fractional Langevin equation. So here we have the inertia term, and then we have a friction term, but the friction now is non-local. We get a friction kernel. And this friction kernel is composed of a series of exponentials, and when the chain becomes longer and longer, this converges because the amplitudes and the frequencies are scaling forms. It converges to a power law form. And then when we impose equilibrium on the system, we have the Kubo fluctuation dissipation relation, and that enforces that the noise-noise correlator actually is coupled to the friction kernel. Okay? And it's still a Gaussian form. And I think yesterday someone mentioned the amplitude. It can be positive or negative, depending on whether the motion encoded in these noise-noise correlations are persistent or anti-persistent. And anti-persistence comes naturally out from this system. Imagine bead I gets a little push to the right. So it immediately experiences a restoring force due to this spring. And a little bit later, a restoring force from the next nearest neighbor, and so on. So it's pushed back. At the same time, the ones to the left, they pull it back. So every motion in one direction is followed by a motion in the other direction. So this is anti-persistence, and when you look at the trajectory, it's extremely jiggly. And the overdamped limit of this process has the same mathematical structure as the much simpler fractional Brownian motion. And in both cases, one can show, this is what Eli did with Weihua Deng several years ago, that in the long time limit, again, we have ergodicity of this process. So this is a very benign process, whatever. We can actually then also ask, what is the convergence to ergodicity like? Now, you know, even when you have Brownian motion, you have a finite trajectory, then we get, in the spirit of what Gleb told us about the power spectrum, also the mean square displacement will have fluctuations in the amplitudes. In a random walk picture, let's say you have a Poisson waiting time distribution, you will have a little bit of a difference in the number of jumps in a certain measurement window. So this will give you an amplitude variation, and we can quantify that with a dimensionless number xi, which is the result for a single realization of a trajectory. I calculate the time average mean square displacement, and then I divide this by the average over all the measurements I do. So when this variable is very, very closely concentrated around 1, it means the process is very highly reproducible. Okay, we will see that there are other cases when it remains, even in the asymptotic limit, it remains very broad. And one way to quantify the width of this function is the so-called Eli-Bar-Chi, or sometimes also called ergodicity breaking parameter, and it's the second moment of this guy minus 1.
So, excuse me, how is it related to what people are calling ohmic, subohmic, superohmic dissipation? Because it's essentially the same equation that people are writing there. I just want to map.
I'm not familiar with that notation. I know that it's around, but
It's just exactly that same analysis.
Possibly. You can teach me afterwards. I know these names, but I'm not entirely familiar with them. Okay. For instance, then one can show that this ergodicity breaking parameter, of course, it decays to 0 with growing measurement time, for instance. Where's my measurement time? Was somewhere. Lost it. The structure then when you get these different alphas that I haven't mentioned so far, because when you have these equations, I forgot to say the mean square displacement goes like this, t to the alpha. So the steepness of your correlation, how it decays with time, is actually then encoding for the anomalous diffusion. Okay, and then you can understand this ergodicity breaking parameter, this variance of the fluctuations as a function of alpha. Let us look at what happens in real systems. Is this actually a good model for what happens? Let us first concentrate on what we see down here. These are results from Line Ollershill's lab at the Niels Bohr Institute for little plastic beads. They're roughly the size of 0.5 to 2.5 microns. She puts them in a viscoelastic solution of worm-like micelles. And then, for instance, what she measures is the displacement correlation function.
and this is encoded here, and you see that this correlator, it goes down to actually negative values. Here is the 0 line. It goes down to negative values and then recovers very slowly. And it's difficult to see probably, projection is not too good, but the data and the black line that you see are right on top of each other. And the black line, that's exactly what we get from these fractional Brownian motion models. And you see there's a perfect match. We can also look, for instance, at higher order moments. We have certain information what their amplitude should be down here. And this also points at fractional Brownian motion, and we can do other analysis. However, Lene can also measure the same particles by an optical tweezer setup. So she puts this more or less harmonic confinement onto the particle. So at the very beginning, the particle is centered in the tweezer in the tweezer, so it doesn't feel confined. It's just moving freely. But eventually, it ventures out and it feels the confinement. And despite the fact that this process is asymptotically ergodic, when you kick it out a little bit of its comfort zone, I don't want to go into the mathematical details, you can actually show that then the relaxation in the harmonic potential is no longer exponential. This is an experiment in water. Here you see the very fast exponential convergence to the thermal value. In the viscoelastic solution, it actually is being replaced by a 1 minus power law recovery. So it's, in this sense, a transient non-ergodic behavior, if you want. When you look at similarly sized objects in real cells, these are typical results that we have. You see high amplitude variations here, but when you plot them with this dimensionless quantity that I defined on the previous slide, you see that it's still a distribution that's pretty much centered around 1. So this will be very different for the non-ergodic processes I will show you afterwards. So we have these kinds of distributions, and when you do analysis of these particles, you will actually get very, very similar anti-persistent motion, and many people in these systems actually showed that it's a viscoelastic behavior that is true for most of the systems that are known in literature. There are exceptions that I will come to afterwards, some more specific systems. What happens when we look at active systems where motor-driven motion plays an important role? This is experiments by Christine Seelhuber in Kiel, and she's looking at very nasty amoeba cells. They're very, very complicated. You have the nucleus here, you have all kinds of vacuoles, and she's looking at the motion of these smaller inclusions. They're lipid inclusions of the order of a few hundred nanometers in size. And the whole thing is swirling around. When you look at images of this thing, then you can see that there's a very concerted motion going on in the cell. And when the cell is happy and they measure the mean square displacement, you see alpha values that are in between 3.5 and 2. So this is really super diffusion, beautiful. But then these experimentalists, they know how to put all kinds of poisons in the cells. They destroy parts of the structure. And for instance, when they put this blebbistatin, this is known to inhibit the action of motors. So all of a sudden, the cell stops moving, and the traces then just wiggle around a little bit around their some mean position. And you can see this is connected with a very, very small value of alpha. So let us look what happens when the alpha is very small. When there's no motors, we see exactly again this anti-persistent motion consistent with this fractional Brownian motion picture. Again, we have this beautiful agreement between theory and experiment. These cells are very nasty, I said. They recover. You leave them there, and they become happy cells again. So you see, you measure the correlation after some time, and eventually it's a completely positive correlation again, and that's exactly what you would expect for a persistent motion. So you can even, that's a beautiful experiment that her student did at that time, and where you see this slow recovery back to superdiffusion. When we look at ex vivo systems, systems that we can simulate, like Denis said about molecular dynamics, we can study a little bit more details. We have a cleaner system at hand. So what you see here, these are kind of the basic elements for biological membranes. These are lipid bilayer
systems where you have that they're composed of lipid molecules with a head group and two tails, and they are self-assemble to a bilayer because the tails are hydrophobic, the heads are hydrophilic. This is the water. So by arranging like this, they exclude the water from the hydrophobic regions. And there are different configurations. I don't want to go into details, but they're kind of three different major phases of these lipid bilayers. And again, when we measure in the simulations, they were done by Matti Javanainen at Ilpo Vattolainen's group in Tampere. And you can again see exactly this anti-persistent motion. In all the three cases, the motion is very reproducible. So all the 128 trajectories we have, they lie one on top of the other when we look at the time average mean square displacement. The fact that this looks a mess is, of course, when the lag time gets close to the measurement time, you can't expect good statistics. So probably we should have just cut it off here. Anyway, so these are good systems. We can show that, I will not go into details, that, for instance, first passage behavior is exponential. That's another clue towards this fractional Brownian motion, this viscoelastic behavior. We also know that after some time, there's a crossover back to normal diffusion, or a crossover to a faster subdiffusion, and one can model it, for instance, by introducing different kind of tempering into this noise correlator. Here you see the power law that we had before. We can have an exponential crossover, we can have a power law, and when you look, for instance, at what happens to the mean square displacement in this system, you see this crossover behavior. And what's surprising to me is that even, this intermediate behavior between theory and the real data from the simulation, it matches perfectly. Don't ask me why it's such a beautiful match. I'm just happy about it. Okay. And experiments show exactly this. So this is scattering experiments. You see this crossover here, in this case, to normal diffusion at long times. There's this intermediate subdiffusion. And they even discovered a short time, very slow subdiffusion that's completely out in the blue. We all don't know what to do with this. So this is state-of-the-art experiments. And now people are thinking how to interpret this very short time behavior. Now let's make a big jump. I will come to the intermediate behavior afterwards. Now let's make a big jump. Now again we look at membranes, but we look at real membranes. So this is what you see here is the trajectory of a single protein channel. It's embedded in a membrane, it's moving, in a living human cell. This is roughly 1 micron. The traces are of the order of minutes. So this is very long, and the reason why they can trace it so long, the cell sits on a cover slide and they monitor from below. So it's a two-dimensional motion during the entire experiment. And what they see, this is experiments by Diego Krapf. He was mentioned a few times before today at Colorado State. And what he sees in the experiment is the particle is fuzzing around vividly, and all of a sudden it gets stuck. And this is related with some complexes. This is biology. We don't want to know all about this. And then after some time it breaks free and it fuzzes again. And those immobilized, those trapping times, they more or less fulfill this asymptotic power law behavior. Now I will show you exact results on the slide afterwards, but what you can see, you have more or less a random walk picture where random walks are interrupted by very long waiting times. And these waiting times, as we see here, they're power law distributed, and the alpha in this power law is smaller than 1. So we have a diverging characteristic waiting time. And when I draw individual events from one of these waiting times, of course, on average, the waiting time becomes longer and longer. And it's not surprising that when we look at the mean square displacement as a function of the measurement time, it's a decreasing function of time. Just the system is aging, it becomes less and less mobile. What's a bit more of a surprise maybe is when we look at individual realizations of time averages, we get a huge amplitude scatter. And of course, individual realizations can now have individual very long waiting times. And they will be a little bit different from one time series to the next. And as there's no scale separating short and long time motion, actually no matter how long I measure, I will have individual events that influence the magnitude of my time series. So time averages, and Ellie has been working on this for a long time, and we then actually look together at what happens for these diffusion processes. These time averages, and for other for other observables, they remain random quantities, but we know their distributions. We can calculate their distributions. I will show you that on the next slide. What you immediately can see then is also that the time and ensemble averages, they don't scale the same anymore. The ensemble average still shows the apparent anomaly delta to the alpha scaling, but when I look at the time average, it's delta to the first power. So you could assume, okay, this is Brownian motion, let's done, finished. And actually, as Gleb said, most experimentalists, they always measure as long as they can, and then they take the data. But if they were taking parts of the data and then looking at the dependence on the measurement time that they analyze, you will see this dependence. That's exactly the aging dependence I argued before. I should also say that in this experiment, in this process, naturally, the distribution is non-Gaussian. You actually get stretched Gaussian behaviors. That's old-fashioned CTRW theory. So these are now results from a paper we had 10 years ago. Well, it's another jubilee. Didn't mention it. 10 years should be written here. It's also Igor and Yossi had a paper in PRL that same year on similar or almost identical results. And we have the time average. What we can show for this continuous time random walk, it's exactly this behavior that I told you about. And if we look at the distribution of the amplitude fluctuations, when alpha is 1/2, for instance, you can show it's exactly a half Gaussian. So 1 here is not is nothing special in this distribution, but you see the maximum is at 0. So this would be 0 motion during the measurement, or 0 amplitude, and then we have a very broad tail. When alpha goes back to 1, here we have 3/4. You see slowly you develop a peak here around the 1, and when alpha is 1, normal diffusion, we have exactly this perfectly reproducible behavior, the self-averaging behavior. When we measure long enough, every trajectory will give me the same amplitude. Another funny behavior is when I confine the whole thing. Again, Lene, she actually did experiments on this again with her optical tweezer in a regime where there is some waiting time behavior as we have in this theory. Now, when we have these time averages, they're very strange quantities. The ensemble average, we know at sufficiently long time, it will just converge to the thermal value. However, a time average, it averages over the free part of the motion and the confined part of the motion, and what you get under confinement, it's not a constant, you actually get a different power law. Now you get delta to the 1 minus alpha. So that's also quite funny behavior. So when you plot the mean square displacement, you have the free part, which is linear in delta, then you have a crossover to 1 minus alpha. And this can be actually seen in experiment. I don't discuss it here. Because there's another effect that we want to look at, and this is aging. So assume that you leave your system, it makes jumps here, every blue impulse would be a jump, and if you let this system evolve, then on average you will have longer and longer waiting periods. And if you then just at one point you start your measurement here, there's a high probability that you will actually find the system in one of these long immobilized periods. And that's exactly what Claude gave us with all these beautiful recurrence time distributions that we used in these derivations here. Now the occurrence of the first jump after this initial after the initialization of my measurement actually has, of course, a different distribution as the individual jumps on the line. And when you actually calculate this, the time average turns out to be a beautiful quantity because this aging time factorizes in the time average. So all the physics is encoded in the delta dependence, whether it be the free motion or the confined motion or whatever. All the dependence on the aging is summarized in a coefficient. That's a very beautiful property. It's much better than when you look at the ensemble average, where you actually see crossover dependencies as a function of TA. Now, is all this relevant, what I'm telling you? You can always say in real systems, power laws always have a cutoff. You have a finite system, you have a longest time scale. So let me give you one example. These are simulations by Jeremy Smith's group in Oak Ridge. And they look at the relative diffusion of 2 amino acids in a protein chain. So we're looking at molecular dynamic simulations of a single protein. And let's look at this image here. So this is the displacement correlator as a function of the lag time. So that's again a time average quantity. And when they take the first 100 picoseconds of their simulations into account, they actually see this, I think, black curve. And then they determine a characteristic relaxation time of the correlator. Then they take a longer part of their data into account. They see this curve, that curve. And when they now plot as a function of the measurement time, the crossover time from the correlation function, they say this power law behavior. So that's, of course, exactly what you translate from your power law waiting times. And they actually identify power law waiting times in the configuration space of these molecules. They get stuck in specific configurations. It's a three-dimensional object, a very complicated thing. And from these kind of exponents, you can understand the behavior, the scaling, the non-stationarity of this correlation function. So they see in the simulation something like, I don't know, 6, 7 orders of magnitude of this non-stationary behavior. And now there happens to be an old experiment by Sunny Shi's group. And when you extend it, you see that, and you assume that, the molecular dynamic simulations, they're good enough, whatever. But it looks like there's a beautiful connection between the experiment done at much longer time scales and the simulations. So the claim in that paper is that in this individual single molecule, you have 13 orders of magnitude of this non-stationary power law waiting time behavior. It's exciting. To me, it's mind-boggling. There's some recent experiments by one of the collaborators of the former paper where they combine experiments and simulations, and they see very similar aging behavior, not 13 orders of magnitude, but I think 8 orders of magnitude for protein-associated surface water. We have other simulations of systems. So this is actually something that can be seen experimentally over many orders of magnitude. So it's not just an artifact of some strange simulation. That's kind of state of the art. We also have non-ergodic behavior, very, very similar. I just flash up 2 different systems. One is relevant to when you look at granular gases, like when you have these little moons and whatever particles around Saturn, or when you, in the morning before you eat your cereals, you put them on a vibrating plate and you see them jumping around. So this would be examples for systems where the temperature of the system, which is defined as the kinetic energy, becomes a decaying function of time, and you get anomalous diffusion, which is non-ergodic and fulfills many, many similar behaviors as the system I just introduced. And interestingly, a very delayed crossover to the overdamped limit. Another system is when you look at something that is a power law function, when the diffusivity is a power law function of the distance or the location, then you also get very similar behavior. You get these non-ergodicities. Probably I skipped this very quickly. You see that the 2 systems I just introduced, when it's time-dependent or space-dependent diffusivity, you get actually the same functional form for the aging dependence. Now, the last few minutes, so I want to come a little bit towards extreme values as well. Let's assume now we have a system where every single step suffers from aging. Let's first look at the right. I was living in Tel Aviv long enough so that this is a very realistic scenario. Let's assume you go to a bus stop and you wait for the bus. And the bus, it started some time before, and let's assume buses arrive with power law delays. So when you have power law delays and you have no characteristic time scale, the later in the day, the longer the time gaps between arrivals of buses. And in Tel Aviv, that's very natural, because bus drivers, they meet at the terminus and they talk endlessly. And then, 10 buses come at the same time after 2 hours, something like that. Joking. Actually, Christian Beck discovered power law delay times of British trains. But here, at least, the mean is finite, but the variance is diverging. So we can actually, let's assume we have, these buses with power law delays. So each time you want to change for another bus, the time is later. So the typical waiting period on average will be even longer. So every
change from one bus to the next you make, you have an even longer aging period of the system. Now, in every step, you have a long delay. And one can think of, or we actually mapped it onto a more microscopic system, which is called a single file system. Let's say we have a channel, we have Brownian particles, and we trace only one particle. And this particle, of course, when it bumps into its nearest neighbors, it cannot move any further. And this is a very famous problem. It was solved by Harris in the late 60s. And he showed that it actually belongs to the class of these fractional Brownian motions. And the mean square displacement goes like square root of time. But now assume you can functionalize these particles, and experimentally it was shown that this functionalization can lead to power law attachment times to walls. So now we have power law waiting times in the system, and now let the system age a little. So now let's say this guy is mobile at this time, but it bumps into its neighbor, and this is during one of these very long immobilization times. So very likely the first step of the neighbor is then dominated again by this aging. Okay, and then you come to the next nearest neighbor, and so on. So maybe qualitatively, I argued that this is actually very similar to waiting for the next bus to come. And one can actually then come up with a whole framework for these aging continuous time random walks that we did with Mikael Lomholt and Tobias Ambjørnsson, both former postdocs of mine, now in Odense in Denmark and in Lund. So we created this kind of waiting time process, and if you then map it onto this single file diffusion with aging waiting times, power law waiting times, you can actually show that this power law, this square root behavior, gets converted into the square root of the logarithm of the behavior. So you get a very drastic slowdown of the motion. An individual particle, a single particle, only this one marked particle, if it were moving in the channel and you were functionalizing it, it would just go from t to the alpha, right? But here, when we have a waiting time, the alpha actually does not get into this logarithm or the square root of the logarithm. You just go to a completely different class of dynamics. The alpha is only then apparent in the local amplitude of your mean square displacement. What I show here is the squared mean square displacement, so I get rid of the 1/2, and then this is linear, this is logarithmic, and so I get this linear behavior in the simulations. Okay, so this is actually the case when alpha is smaller than 1. When alpha is in between 1 and 2, it's the most complicated problem, because when we map the number of jumps to time, it's a sharp distribution when the waiting time is diverging. It's a sharp distribution when it has all moments, but when it doesn't have a variance, it's not a sharp distribution. And we then get a much more complicated behavior for the mean square displacement. Good. How much time do you give me?
Well, we just have to 12.
So let me mention two points following up on Denis' talk. I show you first one experiment. So now I should have, I wanted to put actually a picture here now for something completely different. I have a beautiful picture of Monty Python. Forgot to put it here. So reshuffle your brains quickly. Think about food. No, we think about the talk. Okay, so what you see here is actually a system that was believed to be at longer times perfectly Brownian, normal, diffusive, Gaussian. So these are measurements done by Carsten Bethe at my institute. These are traces of cells moving on the surface. Nothing special about the surface, perfectly homogeneous, and they don't bump into each other. They're measured at different times. It's just that all the data are accumulated in this plot. And so far, all the modeling was thinking of persistent Brownian motion. So you move in one direction preferentially, but then eventually you decouple, and it should cross over to normal Brownian motion. But when we actually analyze the displacement distributions, we see very clear non-Brownian behavior like what you had before. And the funny thing is, when we increase the lag time during which we measure the displacement, it actually becomes more exponential.
That's a very, very odd process. So this is just mere data analysis. We don't have a full understanding. Oops, I don't show it here. One can show that there's a scaling variable for this behavior and so on. So this is actually a very curious behavior. And this is just repeating what Denis said. This is a model we set up to understand this. So we were hearing about diffusing diffusivity, and this is kind of our version where we have, again, the time dependence of the diffusion coefficient that we map onto a square of a process, which is then an Ornstein-Uhlenbeck. And why I don't want to skip it, this is what Denis said before. When you look at the kurtosis, which is measuring the non-Gaussianity, you see exactly this crossover behavior. So this is for the one-dimensional case. You see the value 9 at short times. That's exactly the value for an exponential distribution in one dimension. And the value 3, that's exactly the Gaussian. So you see this crossover very, very pronounced here, and it occurs exactly at the time scale that is given by the relaxation time of the Ornstein-Uhlenbeck process. And the mean square displacement really has the same behavior at all times, short times, long times, so there's not even a crossover of the coefficient. That's the beauty of this model. Actually a very strange property. And of course we have crossover from exponential to Gaussian. The funny thing is we were thinking about all these single molecule experiments. Let's say we have a particle and then we try to put this optical tweezer on top of the particle. And if we're a bit clumsy, we suck it in more or less. So we have a local distortion of equilibrium. So it does make sense to us to think of a non-equilibrium initial condition, and then we actually change this behavior. So before, when we start with an equilibrium distribution of the diffusivities, we have this perfect linear behavior, and here we get crossover behaviors depending on the value of the initial, depending on the initial value of the diffusivity. For instance, when it's 0, the system, the diffusion first has to heat up, so it actually leads to a ballistic motion that then crosses over to normal. And we also generalize the non-Markovian behavior based on a generalized Langevin equation, where we introduced then some kind of a super statistical model that was work with Jakub Schlenzak earlier in the year. And indeed, Gaussian behaviors are found in living cells. I just want to show you this here. This is the distribution of diffusion coefficients measured in individual trajectories in bacteria and in yeast cells. So indeed, it's important even in relatively simple cells. So David, I have no clue, where all the heterogeneity comes there from. A bacteria cell is a relatively clean system, and the yeast cell is actually an even cleaner system. So, but again, they measure these individual behaviors and then get these exponential tails.
Does it reflect stochasticity with time, or does it reflect different properties of different diffusing particles?
The paper claims both. The paper claims, I haven't seen the data. So in the paper they claim they see this distribution when they analyze individual time series, and they see it when they compare different time series. So that's the statement of the paper. Okay. What we see, for instance, from these the cells, there I'm pretty sure it's behavior of different cells. They all have a different degree of happiness. Yeah. Okay. There I'm pretty sure. Here I can't tell you. Good. And again, when we look at the well-defined system, we go back to the simulations. That's what I meant before. We go in between the very dilute and the real cell system. When we crowd the cell with big protein chunks, we also see non-Gaussian behavior. And especially here we can see to some extent where this non-Gaussianity could come from. We actually see that there's intermittent motion. This is in the pure lipid cell, the situation that I showed earlier. When I look at the momentary diffusivity, it looks like a very stationary process. And for individual trajectories, we see a very clear, very narrow distribution of the diffusivities. Once we crowd the membrane, you see intermittent behavior. Very low values, and this corresponds when the lipid is trapped in between proteins and has a hard time coming out, and you see it's much broader. And actually the same behavior you also see from simulations with purely excluded volume interactions. Good. And experiments in cells, in living cells, they actually see exactly again exponential tails of the displacement. So it's not just something from our fantasy and simulations. You can see it in real experiment. Last slide, I promise. Then I'm done. Now, finally, something on real extreme value statistics. This is work that was just submitted together with Ido Eliazar and Shlomi Reuveni. We heard a lot about the three different classes of extreme value statistics before. We had Gamble, Frechet. What's the third one? I'm getting tired. Gamble, Frechet, and Weibel, exactly. And they typically come out depending on the setting, how you define your extreme value problem. What's the input? But now think of a dual extreme value principle. So here I have a schematic. Let's say I have random entries in a matrix. And the first thing I do, I compare pairs of entries. I compare entries in these columns. And in each case, I take the minimum value. But then I look at this matrix. And out of these minimum values, I take the largest. So first I take a minimum principle. And then I take a maximum principle. I don't know, you can think of, you have a long bridge consisting of the same elements, and you want to know what's the maximum you can trust the bridge, right? You first look at the weakest link of each bridge, and then you look what is still the best of these bridges that I could expect. Or you can think of, you have a series of cells, they divide, and you want to, you know that you have a weakest element in there. And then out of the weakest links, when you look at the cell line, you want to kill the cells with an antibiotic. But then you want to know what is the minimum of antibiotics I have to put in there. So out of the weakest links, I need to know the strongest one. Okay? And in these cases, when you have this dual extreme value, actually what comes out is that Gamble is universal. That's the message of these studies. And you see here this Gamble distribution. It comes out for any kind of distribution that we plug in. Gamma, exponential, beta, blah, blah, blah. In all the cases, it actually turns out to be the Gamble distribution. This is on the archive. You can look at it. There's a few papers I want to refer to. There's some review articles. This is with Lene. Which is very experimental if you really want to know about experiments. But there's beautiful, beautiful schematics that Camilla actually came up with, and some of the theory. The mathematical definitions and the properties of these anomalous diffusion models, the ergodicity breaking, the aging, you can find in this review article from a few years back. A beautiful article together with my former PhD student, Johannes. He then wrote some very beautiful papers with Eli as a postdoc about the aging renewal you can find here. And then this is about the stuff in the membranes. And this I didn't talk about, the translocation through nanopores. Lunch is up, I guess. Thank you.
So thank you very much. So there still should be questions for the talk, even though some already start running for lunch.
Gleb, gleb, gleb.
No?
Hunger. Okay.
Okay, thanks a lot.